Welcome back to the deep dive. Now, usually you know the drill.
Right.
We take a stack of articles, we read them for you, we synthesize the shiny takeaways,
Right.
and we give you the dinner party version of the truth.
We make you smart fast. That is the standard operating procedure. Efficiency is usually the goal.
Usually.
We curate, we trim, we present the highlights.
But not today. Today, we are initiating something different. We are initiating the unabridged protocol.
The unabridged protocol, it sounds intense.
It is intense. It means we are not summarizing. We are not skipping the hard parts. We are not breezing past the equations that look, like hieroglyphics.
So we have a single document in front of us.
Exactly. A research paper titled Irrationality of Rapidly Converging Series, a Problem of Erdős and Graham.
And look, to be clear for you listening, this isn't just us being pedantic for the sake of it. This paper is special.
It's a landmark.
It is. It's the result of a collaboration between human mathematicians and Google DeepMind's AI, specifically an agent called Alethea, which is powered by Gemini DeepThink.
And they solved a problem that has been sitting open, unsolved, since 1980.
For decades.
So the mission is simple but grueling. We are going to read this paper linearly,
Start to finish.
from the title to the final email address in the footer. If we hit a concept, we stop, we verify it, we visualize it. We are operating on infinite time.
No glossing over. I mean, if we see a limit inferior, we are going to live in that limit inferior until we understand exactly why it's there, not just what it is.
Exactly. If we see a citation, we understand its context. So let's begin. Part 1, the header and abstract.
Okay.
I'm looking at the title right now. Irrationality of Rapidly Converging Series, a Problem of Erdős and Graham.
All right, let's parse that before we move a single inch further. Irrationality.
So this is the destination, right?
Yeah.
This is the goal. We are trying to prove a number is irrational.
Right. And in the world of numbers, you have the rational ones, the orderly ones. Any number you can write as a fraction, P over Q, where P and Q are nice, clean integers.
1/2, 3/4.
Exactly. Even 100 over 3. They are rational. They represent a ratio of two whole things.
And then you have the chaotic ones.
The irrationals.
Pi, the square root of 2.
You cannot write them as a fraction. They're decimal expansions. They go on forever and they never repeat. They are wild. They can't be contained by simple integer division.
So this paper is looking at an infinite sum, adding up an infinite list of tiny, tiny numbers, and asking, does the total pile land on a clean, rational fraction?
Or does it drift off into that irrational wilderness? That's the fundamental question.
And the second part of the title, Rapidly Converging Series.
So converging just means the sum doesn't explode to infinity. It actually settles on a specific value.
It adds up to something.
It adds up to something, but rapidly is the key constraint here. It implies the terms we're adding up are shrinking fast. Very, very fast.
Like if you add 1/2 plus 1/4 plus 1/8, that feels fast.
It is. But here we're talking about terms that shrink so aggressively that the sum barely moves after the first few terms. The action is all at the beginning.
And finally, a problem of Erdős and Graham.
The heavy hitters, Erdős.
The man was a legend.
The most prolific mathematician of the 20th century. A man with no home. He lived out of his suitcase, traveled from university to university, crashed on colleagues' couches, and just wrote papers.
He famously referred to children as epsilons.
Right, because in math, epsilon represents an arbitrarily small positive quantity. That was his sense of humor.
And Ronald Graham.
A giant in his own right. In combinatorics, and famously, a professional juggler. He was one of Erdős's closest collaborators. And in 1980, they wrote this book of open problems.
And this paper solves one of those problems.
Question number 1, in fact. The very first one.
Okay, so completeness check. Have we fully defined the scope of the title? Just those few words.
I think so. We have irrationality, which is chaos versus order. We have rapid convergence, which is about shrinking terms.
Yeah.
And we have the historical provenance, 1980, Erdős and Graham. Yeah, I think we are clear to proceed.
Okay. The author list. Kevin BARRETO, JIWON Kang, SANG-HYUN Kim, VJEKOSLAV KOVA:C, and SHENGTONG Zhang.
And just take a moment to look at the affiliations, which, we'll see at the bottom later.
Okay.
You've got Cambridge, Seoul National University, KIOS in Korea, University of Zagreb in Croatia, Stanford in the U.S.
It's a global team.
Absolutely. Mathematics doesn't really care about borders.
All right, moving to the abstract. This is usually the summary, but for us, it's the map for our journey.
It's the mission briefing.
Sentence 1. Answering a question of Erdős and Graham. We show that the double exponential growth condition, and immediately we hit our first mathematical roadblock.
Stop. Double exponential growth. We need to feel the weight of that.
Okay, so standard exponential growth is something like 2 to the n.
Right. So you get 2, 4, 8, 16, 32. It gets big pretty fast.
But double exponential is different.
It's 2 raised to the power of 2 raised to the power of n. So if n is 5, regular exponential, like you said, is 32. Double exponential is 2 to the power of 32.
Which is a big number.
It's over 4 billion. It grows terrifyingly fast. The paper is claiming that this specific violent rate of growth is the key to everything.
So now let's read the condition itself. It's a limit supremum.
The text presents the following expression. I'll read out the LaTeX code first, just for absolute precision, and then the English translation.
Okay.
The LaTeX is 4, 5 and 1, 5.
And phonetically for the TTS.
The limit as n approaches infinity of a sub n raised to the power of 1 over phi to the n equals infinity.
Okay, we are going to spend some time here.
Oh, we have to.
So a sub n is our sequence of integers. These are the numbers we're eventually going to use in our sum.
Right, they're the building blocks.
And phi. That's the golden ratio.
Yes, phi. Approximately 1.618. It's the number you get from the ratio of consecutive Fibonacci numbers. It shows up in nature, in art, and surprisingly often in number theory.
But why here? I mean, why is the golden ratio showing up in a problem about infinite sums?
That is the deep magic of this paper, and we'll see it unfold. The golden ratio is often called the most irrational number.
What does it even mean?
It means it's the hardest to approximate with simple fractions. So it sort of represents a fundamental boundary of irrationality. Here, it's acting as a threshold.
So what is the expression doing?
It takes the nth term, a sub n, and it takes the root of it, specifically the phi-n root.
It's a kind of root test, like from calculus.
Exactly. It's checking how heavy the tail of the sequence is relative to this power of the golden ratio. If this limit goes to infinity, it means a sub n is growing much, much faster than phi to the n.
So if it were growing at the same speed as the golden ratio, this limit would be, what, a constant?
A constant, yeah. But since it's infinity, our sequence is it's outrunning the golden ratio by a massive margin.
Okay. The abstract continues. For a monotonically increasing sequence of positive integers.
That's a simple one. Monotonically increasing just means no backtracking.
Every number is bigger than the last one.
Correct. A sub 2 is bigger than a sub 1, a sub 3 is bigger than a sub 2, and so on. It ensures we're always moving forward. The numbers are always getting bigger.
Now, the abstract adds a second condition, together with the bound. And we have an inequality.
Okay, let's read it carefully.
The expression is 1n plus 1 plus 1 plus tau.
And phonetically.
A sub n times a sub n plus 1 is greater than or equal to n to the power of 1 plus tau.
Okay, so this is a bound on the product of neighbors. It says if you multiply 2 consecutive terms, a sub n and its partner, a sub n plus 1, that product has to be growing faster than n raised to some power slightly bigger than 1.
And that's the tau part. The text says where tau is greater than 0.
Right. Tau just needs to be some tiny positive number. It could be 0.1. It could be 0.00001, as long as it's not 0.
So what's its purpose?
It prevents the sequence from stalling out. It ensures that the product of terms isn't just growing linearly, like n, but has a little extra kick. It's growing superlinearly, even if just barely. It's another growth condition, but a much weaker one.
And if both of those conditions are met, the big double exponential growth and the smaller product bound, the paper claims something about the sum.
And here's the target, the sum they're looking at. The LaTeX is int1 and int sin n plus 1 phenix.
Identically, that's the sum from n equals 1 to infinity of 1 over the quantity of sub n times a sub n plus 1.
So if those growth conditions are met, this specific sum is an irrational number. That is the core claim of the paper.
So if the numbers get big fast enough in this very specific way,
the sum cannot possibly settle into a rational fraction. The tails of the sum, the tiny bits you add on at the end, they become too sparse, too erratic to ever fall into the kind of repeating decimal pattern that you need for rationality.
The abstract goes on. We also provide a positive generalization too, and it references a theorem 3.
Ah, theorem 3, that's the monster. We'll get there in section 2, but just as a preview, it generalizes this result from just pairs of terms like an times an plus 1 to longer strings of terms.
And it also mentions a negative result.
In math, a negative result isn't bad news.
Right, it's not a failure.
Not at all. It's a boundary. It means they show their result is optimal. They prove that if a sequence grows any slower than the threshold they found, then the sum actually could be rational. They found the precise tipping point between order and chaos.
And the final sentence of the abstract, this is the one that made headlines, or, the headlines in the math world at least.
Mm-hmm.
The original problem was autonomously solved by the AI agent Alethea, powered by Gemini DeepThink, while the remaining material is largely a product of human-AI interactions.
Autonomously. That is the heavy word there. It implies the AI didn't just act as a fancy calculator.
It wasn't just checking arithmetic.
No. It implies it navigated the search space of possible proofs. It made strategic decisions. It found the route.
Okay, completeness check. The abstract is incredibly dense. Did we miss any nuance?
I don't think so. We covered the two growth conditions, the definition of the sum, the crucial role of the golden ratio, the generalization, the negative optimality result, and the AI attribution. I think we're complete on the abstract.
Good. Let's proceed. Part 2. Section 1. Declaration of AI usage.
This is already unusual formatting for a math paper.
Very.
Usually, software tools or computational assistance gets buried in the acknowledgments or a footnote, like, we use Python to check this calculation.
Right, yeah.
Here it is section 1. It is front and center. They want you to see this.
Paragraph 1. The present paper resolves a problem posed by Paul Erdős and Graham. Beyond the mathematical result, this work is also notable for its methodology, which relies heavily on artificial intelligence in a collaborative effort with Google DeepMind.
They are explicitly signaling a paradigm shift. This is a methodology paper as much as it is a number theory paper. They're saying, look at how we did this. The how is as important as the what.
They then break the timeline down into points 1 through 6. We're going to walk through this granularly because this is really the story of the discovery.
Agreed. This is the narrative.
Point 1. The 1980 context. Erdős and Graham posed question 1 in their problem book, and they expressed a belief that it should be solvable, perhaps by, and this is a quote, standard tools.
Standard tools is classic mathematician speak for, we shouldn't need to invent a new branch of calculus to solve this.
Right. The tools are in the shed already.
Exactly. They thought it was within reach.
But they were wrong.
Apparently so. I mean, it sat unsolved for almost 45 years. That suggests that while the tools might have been standard, the specific combination of them, the path through the maze, was incredibly subtle.
A path that no human had stumbled upon.
Correct.
Point 2. Alethea, a custom math research agent built on top of Gemini DeepThink, found a solution to question 1.
So let's dig into Gemini DeepThink. Most people now know large language models, right? The chatbots everyone uses.
Mm-hmm.
They are, at their core, incredibly sophisticated autocomplete engines.
Yeah.
They guess the next most probable word. And this is why they're generally terrible at math. They hallucinate. They guess numbers rather than calculating them.
But DeepThink implies something else is going on here.
It implies a system that performs some kind of tree search or chain of thought reasoning. It explores a logical path, verifies if it makes sense, backtracks if it hits a dead end, and tries again.
It's closer to how a human plays chess, thinking several moves ahead,
than how a parrot mimics speech.
Yes.
And the text notes something fascinating here. It says, from the original output, it was clear that some generalization was possible. Specifically, the proof used rough estimates such as 1.72, log x, etc.
So this is the messiness of the AI.
It is. The AI found a path through the dark forest, but it didn't stay on the nice paved trail. It just smashed through the bushes.
It said, well, 1.7 is less than 2, so that's good enough for this step. Move on.
Exactly. A human mathematician might try to be elegant. They'd search for the tightest possible bound. The AI just bulldozed through with estimates that were sufficient, even if they weren't pretty.
But it worked.
It worked. It found the proof. It prioritized true over beautiful.
Point 3. The authors realized and proved that one can relax the original growth condition and generalize the series. This generalization is now formulated as part 1 of Theorem 2.
So the AI cracked the door open. The humans walked in, looked around, and said, wait a minute, we can actually make this room bigger. They relaxed the conditions.
They made the theorem stronger.
By cleaning up the AI's messy bounds, they made the result apply to a wider range of sequences.
Point 4. Gemini DeepThink discovered a further generalization, and then, jointly with Alethea, proved it. This generalization corresponds to Theorem 3.
This is the ping-pong effect. It's the collaboration in action.
Humans improve the AI's result.
They feed it back to the AI. The AI then says, oh, if we can do that, then we can generalize even further to this monster result, Theorem 3.
Which we'll see later is the one with the arbitrary weights.
Right. It's a collaboration where each party escalates the other's capability. It's a feedback loop.
Point 5. The authors found counterexamples that tightly complement the previously mentioned result.
And this is the game of mathematics. You prove X. Then you have to ask, is X the best possible theorem?
You have to test the boundaries.
To prove that it is, you must find a counterexample that shows if you tweak the conditions even a tiny bit, the whole theorem breaks. The humans found that breaking point.
Point 6. Finally, inspired by Erdős 4, the authors were able to weaken the hypotheses further to obtain Theorem 3 below.
So they went back to the source. They looked at one of Erdős' own papers from 1975 to find the final key to polish the final result into its strongest form.
Okay, the closing paragraph of Section 1. Thus, the theorems and proofs in this paper are largely products of human-AI interactions. In particular, the AI discovered the formulation of Theorem 3 after the human authors presented Theorem 2.
And that reverses the typical narrative.
How so?
Usually humans formulate the theorem, they have the conjecture, and then they might use computers to check it or find examples. Here, the AI formulated the theorem. It proposed the hypothesis.
The text ends with the necessary disclaimer. However, we emphasize that the writing of the paper was entirely done by the human authors.
Right. The ideas are a hybrid, but the prose is human. The narrative structure, the explanations, the flow, that is still the domain of the authors.
Okay, completeness check. Have we fully mapped the human-AI workflow here?
I think so. We've got the timeline. Problem from 1980 AI finds a messy solution. Humans refine and generalize it. AI takes that and generalizes it even further. Humans find the sharp boundaries with counterexamples, final polish using historical context. The workflow is clear.
Let's move on. Part 3, Section 2, Introduction.
Okay, now we get to the formal definitions. This is where we start building the machinery.
The following question was formulated by Erdős and Graham, Question 1. So this is the original 1980 question, verbatim.
Let's hear it.
We ask, is it true that if a 1 is less than, a 2 is less than, and so on, it's a sequence of positive integers with? And here is the original condition. Latex is Widom IFT and 12.
Infinite.
The limit inferior, as n approaches infinity of a sub n, raised to the power of 1 over 2 to the n, is greater than 1.
Okay, pause. We absolutely need to talk about limit inferior.
Yeah, why inferior? Why not just limit?
Okay, so think of a sequence of numbers that wobbles. It goes up, it goes down, it fluctuates forever. If you ask for the limit, the answer might be it doesn't exist because it never settles on one single number.
Okay, like sine of x or something.
Exactly. But the limit inferior is different. It's a more patient question. It looks at the tail of the sequence, so everything from some point n onwards into the infinite future, and asks, what is the lowest value in this entire future?
The absolute minimum from here on out.
The infimum, technically. And as you move on forward, as you look further and further down the tail, that lowest value might start to climb up. The limit inferior is the ultimate floor that the sequence eventually stays above.
So it basically says, eventually, after some point, the sequence never, ever drops below this line again.
Precisely. Even if it wobbles above it, it never dips below 1. And the exponent here is 2 to the n.
Why 2 to the n? Not phi to the n like in the abstract.
Because this was the original 1980 formulation. It's related to things like Ahmes series. The idea is connected to squaring. If you have a sequence where the next term is roughly the square of the previous one, so an plus 1 is like an squared.
The exponents double each time.
The exponents double. You get x, then x squared, then x to the 4th, x to the 8th. That doubling in the exponent is where the 2 to the n comes from. Erdős and Graham were thinking about that kind of growth.
The paper proves a stronger result using phi, but this was the starting point.
This was the seed.
The question continues, and here's the sum. The latex is the m50 for ant 1 and an plus 1.
And phonetically.
The sum from n equals 1 to infinity of 1 over a sub n times a sub n plus 1.
So the original question was, if the sequence grows with this double exponential 2 to the n rate,
is this specific sum necessarily irrational?
And the paper's answer is a resounding yes. In fact, it's yes even under weaker conditions.
The text then goes on to mention Ahmes series and Cantor series.
We touched on Ahmes. That's just summing reciprocals, 1 over an. A Cantor series is a bit more complex. It's a generalized way of representing numbers.
How does it work?
It looks like this. The latex is sum in 50 frec AMJ1A2.
So phonetically, that is, the sum from n equals 1 to infinity of b sub n over the product a sub 1 through a sub n.
Right. It looks a bit like a decimal system. In decimals, the denominator is 10, 100, 1,000, powers of 10.
It's a fixed base.
A fixed base. In a Cantor series, the denominator is the product of a changing base. It's a 1, then a 1 times a 2, then a 1 times a 2 times a 3. It's a much more flexible system for writing numbers.
And the authors note that previous results by mathematicians named Hanel and Tiedemann could solve problems like this if there were specific divisibility conditions.
Right. Divisibility makes things much, much easier. If you know that an divides an plus 1 perfectly, the math is cleaner. You can combine fractions easily.
But Erdős and Graham didn't assume divisibility.
No, they just assumed growth. And proving irrationality based solely on how fast the numbers get big without knowing anything about their factors is much, much harder. That's the challenge here.
Okay, now we hit Theorem 2, the first big result from the humans after the AI's initial breakthrough. Fix a positive integer d and let phi be greater than 1 be the unique positive solution to. And here comes the polynomial.
This is the generalization. The latex is p sid taxed a1 plus 11y.
And phonetically, psi to the d equals pa psi to the d minus 1 plus 1.
Okay, let's make this concrete. If d equals 2, what is this equation?
If d equals 2, you plug it in. You get psi squared equals pi minus 1 equals 0.
That's the quadratic equation for the golden ratio.
Exactly. So for d equals 2, this special number pi psi is just our old friend phi, approximately 1.618.
So why does d matter? What is d?
D is the number of terms we are multiplying in the denominator of our sum. In the original problem, we had an times an plus 1.
That's 2 terms, so d equals 2. Precisely. So the golden ratio governs the irrationality of sums of reciprocals of pairs of terms.
Now, Theorem 2, Part 1. If, and here's the condition, the latex, limdi n1 theoretek.
And phonetically,
The limit as n approaches infinity of a sub n raised to the power of 1 over pi solid to the n equals infinity.
then
Then the sum involving d terms is irrational. The latex for that sum is sum in 50, fac 1 plus 1 dots, n plus d minus 1.
And phonetically, the sum from n equals 1 to infinity of 1 over a sub n times a sub n plus 1 through a sub n plus d minus 1.
So let's connect the dots. If you are multiplying 3 terms in your denominator, so d equals 3.
Then the growth rate required for irrationality is determined by the root of the cubic equation psi cubed equals psi squared plus 1.
A sort of super golden ratio.
You could call it that. As you add more terms to the denominator, as d gets bigger, the growth requirement actually changes. The base CI gets smaller, closer to 1.
Wait, the required growth rate gets slower? That feels backwards.
It's because the denominator is getting heavier on its own. Since you're multiplying more big numbers together, the denominator grows faster by default, so the individual terms don't have to grow quite as violently to achieve the same overall effect.
Oh, okay. That makes sense. Then we have Theorem 2, Part 2. This is the counterexample part.
The boundary.
For every c in the interval 1 to infinity, there exists a strictly increasing sequence, such that the infinite sum is a rational number.
This tells us the theorem is tight. You cannot lower the bar. If you don't meet that limit condition, if your growth is just a little bit slower, then all bets are off. You might land on a rational number. They found the sharp dividing line.
Okay, completeness check. Have we fully unpacked Theorem 2?
I think so. We've connected CI to the golden ratio for the D2 case. We established the relationship between the number of terms, D, and the required growth rate. And we've acknowledged the counterexample that makes it a sharp result. Yes, we're good.
On to Theorem 3, the generalization. This is the one the AI really helped formulate.
Okay, brace yourself. This one allows for arbitrary powers of terms in the denominator.
So instead of just an times an plus 1,
You could have an squared times an plus 1 cubed. It allows us to weight the terms differently. It's much more flexible.
fix a positive integer d and a tuple of non-negative integers, w equals w sub 0, w sub 1, w sub d minus 1.
These are the weights, the powers. So W tells us the power of each term in our product.
And to find the new growth constant, we need to define a special polynomial p sub w of x.
This is what determines the new growth constant. The latex is pw x1 x1 sum d0 wj xj w xd01.
Okay, phonetically that's p sub w of x is defined as the quantity x minus 1 times the sum from j equals 0 to d minus 1 of w sub jx to the j minus capital wx to the d minus 1.
That is a mouthful. But conceptually, it's just a weighted version of the polynomial we saw before. Capital W there is the maximum of all the weights, and C sub W is the unique positive real root of this polynomial.
So just like the golden ratio was the special root for the simple case.
This C sub W is the magic number for this specific combination of powers. If the sequence grows faster than roughly C sub W to the power of n, the sum is irrational.
And the condition in Theorem 3 says, the latex is lim sub W in.
And phonetically,
The limit supremum as n approaches infinity of a sub n raised to the power of 1 over C sub W to the n equals infinity.
now notice it's limit supremum now, not limit inferior.
Right. We did inferior. What is supremum?
Okay, so if limit inferior was the rising floor, limit supremum is the oscillating ceiling. It looks at the tail of the sequence and asks, what is the highest value in this entire future?
The maximum value.
The supremum. The limit supremum is the value that the peaks of the sequence keep coming back to.
Well,
And by switching to limit supremum, the condition becomes weaker.
weaker. How so?
It means the sequence only needs to grow super fast occasionally. It just has to have these peaks that shoot up to infinity. It doesn't have to stay up there. It can fall back down in between.
Wait, but if the condition is weaker, doesn't that make the theorem stronger?
Yes, absolutely. If I say, you must run 10 fair at all times to win a prize, that's a very hard condition.
Right.
But if I say, you only need to hit 10 fair occasionally, infinitely often to win, that's much easier to satisfy. By proving the result holds under this weaker supremum condition, the theorem applies to a much wider, more misbehaved class of sequences. It covers more ground.
Okay, completeness check. Is the definition of Theorem 3 clear? The big one.
I think so. We have the weights W, the polynomial P sub W that's built from them, the special root C sub W that comes from the polynomial, and the crucial transition to a weaker limit supremum condition. It generalizes everything that came before it. Yes, we're clear.
Okay, we'll skip over remark 4 for now. It's a bit technical, and look at Theorem 5, the negative counterpart.
This is the other side of the coin. It defines the boundary from the other side. It defines a slightly different polynomial P tilde W of X.
Let's see it. The latex is tilde PWX. A closed one, sum G D do B J X dash D1.
And phonetically that's. P tilde sub W of X is defined as the quantity X minus 1 times the sum from J equals 0 to D minus 1 of W sub J X to the J minus X to the D minus 1.
So what's the difference? The original polynomial subtracted a term with capital W, the maximum weight.
Right, it had W times X to the D minus 1. This one just subtracts X to the D minus 1, which is like having a weight of 1.
And this slight change produces a different root, a smaller root, C tilde sub W.
Exactly. And the paper says if your sequence's growth is only related to this smaller root, you can actually construct a sequence where the sum is rational.
So there's a gap between the irrationality C sub W and this potential rationality constant C tilde sub W.
Precisely. In between those two numbers is a kind of no man's land where this paper's methods don't say what happens. But below C tilde sub W, rationality is possible. This theorem defines the safe zone for constructing rational sums.
Okay, example 7 makes this concrete. Let's say our weight tuple is W equals 1, 0, 2, 1.
Okay, so that corresponds to a term in the sum that looks like 1 over an to the first power times an plus 1 to the 0 power.
So the an plus 1 term just disappears.
Right. Times an plus 2 squared times an plus 3 to the first.
Yeah.
So simplified, it's 1 over the quantity an times an plus 2 squared times an plus 3.
And for this specific case, they calculate the two roots. The irrationality one is C sub W, which is approximately 1.914, and the rationality one is C tilde sub W, which is approximately 1.345.
So look at that gap. If your sequence grows like, say, 1.92 to the power of n, this theorem guarantees the sum is irrational. But if it only goes at 1.34 to the power of n, then Theorem 5 says it's possible it could be rational.
This numeric gap illustrates the precision of the paper. They didn't just say it grows fast, they put a number on it to 3 decimal places.
They found the boundaries.
Completeness check. Do we understand the gap?
Yes. C sub W guarantees irrationality.
Yep.
C tilde sub W allows for rationality. The gap between them is the boundary region. We're good.
All right. Part 4. Section 3. Proof of Theorem 3. This is the core.
We are entering the engine room. This is where the actual math happens.
We utilize a classical irrationality criterion, Lemma 8. It's attributed to Mahler.
Kurt Mahler, titan of transcendental number theory. And his criterion is a beautiful, powerful tool for proving irrationality. It's a proof by contradiction.
Let's walk through the logic slowly. First, we assume the opposite of what we want to prove.
Right. We assume our sum, what's called S, is a rational number. So S equals P over Q for some integers P and Q.
Okay, so if S is rational, and you take a partial sum, just adding up the first n terms, the difference between the full infinite sum and that partial sum is the tail. It's the leftovers.
And if the full sum is a fraction and the partial sum is a fraction, then their difference, the tail, must also be a fraction.
Right, and if you multiply that fractional tail by a big enough integer, let's call it d sub n, which is usually the common denominator of everything, you should clear the fractions and get a whole number. An integer.
Correct. And here is the kicker. If that integer is not 0, what's the smallest it can be?
Has to be at least 1.
Exactly. Integers are discrete. They are quantized. You can't have an integer that's 0.00001. If it's a non-zero integer, it has to jump straight to 1 or next one.
And Mahler's criterion formalizes this. The latex is dn, dnn, s sum n, 0, 1.
And phonetically, that is. The limit inferior as n approaches infinity of d sub n times the absolute value of s minus the sum from n equals 1 to n of z sub n is greater than 0.
So what does that mean in words?
It's basically saying, if s is rational, then this quantity we're looking at, which represents that integer, must eventually be bounded away from 0. It must be at least 1, so the limit has to be strictly positive.
So the strategy of the entire proof is to show that for our specific series, this limit is actually 0.
That's the whole game. We are going to prove the limit is 0. If we prove it is 0, we contradict Mahler's criterion. If we contradict Mahler, our original assumption that s is rational must be false.
And therefore, s must be irrational.
We are trying to crush that limit to 0.
We are hydraulic pressing it.
Exactly.
Completeness check. Do we grasp the contradiction strategy?
I think so. Assume rational implies, Mahler says, the limit is greater than 0. We will then prove the limit is equal to 0. This creates a contradiction, which means our assumption was wrong, so the number must be irrational. The strategy is confirmed.
All right, lemma 9, Borel's trick.
This is a neat little tool for dealing with sequences. It's about peak indices. If a sequence grows very, very fast, there have to be certain moments, certain indices n, where the sequence is significantly larger than everything that came before it.
Like a new all-time high.
Exactly. These are the peaks. And this lemma proves that the set of these peak indices, which they call script p, has to be an infinite set.
Why do we need an infinite set of peaks?
Because we're going to run our limit argument along these specific peak indices, we might not be able to prove the limit is 0 for every single n going to infinity. But for a limit inferior to be 0, we only need to find one subsequence that goes to 0. The peaks provide that special path. They act as our stepping stones across infinity.
Okay, lemma 10, dyadic block estimates.
This is a more technical tool. When you have an infinite sum, a common trick is to chop it up into blocks whose sizes are powers of 2. That's what dyadic means.
And the notation they use here is the double less than sign.
Right. The latex is VFSX LLLX Dale.
Which phonetically is. F of x is Vinogradov bounded by g of x.
It just means f of x is smaller than some constant times g of x. It's a convenient shorthand for an upper bound, hiding an unimportant constant.
So what are the estimates?
Part 1 says if the terms grow at least like k to the 1 plus tau, the sum of the tail is small. Part 2 says if the terms grow exponentially, like e to the k, the sum of the tail is even smaller.
And we need these estimates to control the tail of the series.
Yes. Remember, our whole goal is to crush the tail to 0, and lemma 10 gives us the quantitative tools we need to do the crushing.
Completeness check on these lemmas. Are the estimates solid?
They are. They're pretty standard tools from analytic number theory. Grouping terms into blocks and bounding them is a classic technique. We can accept these.
Okay, now we're setting up the main proof. They define a new variable, mu sub n, the latex, log and cn nu.
Phonetically, that's mu sub n equals the natural log of a sub n divided by c to the n.
So what is this measuring?
It's basically measuring how much the sequence of sub n exceeds the baseline growth rate of c to them. Since our main assumption is that the limit supremum is infinity, we know that this mu sub n gets very big, infinitely often.
Okay, they also define x sub n as the heavy denominator term, and d sub n as the big common denominator for the first n terms. The latex for d sub n is d sub n do, d sub n, and k rather.
And phonetically, d sub n equals the product from k equals 1 to n of a sub k to the power capital W.
This d sub n grows absolutely huge. It's a product of big numbers raised to powers.
And that's the central tension of the proof. We have to fight this huge growth of d sub n with the even faster shrinking of the tail, which they call R sub n. It's a race to infinity. Does the denominator grow faster, or does the tail shrink faster?
And Proposition 11 states the target. This is what we need proof. The latex. Limit if dn rn 0, 0.
Phonetically, the limit inferior of d sub n times r sub n is 0.
This is exactly what contradicts Mahler.
This is the finish line. If we prove Prop 11, we prove Theorem 3.
And to do that, they need lemma 12. The inequality. This looks scary.
It is the magic key that was likely discovered by the AI and then refined by the humans. It creates a surprising relationship between the product of terms, which appears in d sub n, and the very next term in the sequence, x sub q plus 1.
The expression is latex ap dots aq plus 1 clog q plus 1 flight.
In the phonetic version, the quantity a sub p through a sub q to the power capital W times x sub q plus 1 is bounded by a sub q plus 1 to the negative 1 over q squared plus 1.
Okay, let's break that down. Look at the right-hand side. It has a negative exponent.
That means it's a very small number. It's essentially 1 over a sub q plus 1 raised to some small power. And since a sub q plus 1 is huge, this is incredibly tiny.
And the left-hand side is roughly our big denominator, d, times the first and most important term of the tail.
And this inequality says that huge thing is actually less than this incredibly tiny thing.
This is the crushing moment.
Yes. This is the lemma that proves the tail shrinks so much more violently than the denominator grows that the race is won by the shrinking tail. It's the core of the argument.
Okay, so now we get to the proof of Proposition 11. They divide the problem into 3 cases. Case A, Case B, and Case C.
A classic divide and conquer strategy.
Case A. This is when the sequence grows fast enough often. Specifically, the next term, x sub n plus 1, is just absolutely massive compared to the denominator d sub n.
This is the easy case. If the next term is that huge, then the tail r sub n, which is dominated by 1 over x sub n plus 1, is ridiculously tiny.
So d sub n times r sub n is like a big number divided by an even bigger number.
Right. It goes to 0 trivially. Case A is the easy win.
Okay, Case B. This is when the sequence grows, at least exponentially, like a sub n is greater than or equal to e to the n, and we happen to be at one of those peak indices we talked about.
Here we get to use the magic key, lemma 12. When you're at a peak, the current term dominates everything that came before it, which is exactly the setup needed for lemma 12 to kick in.
So the logic we just discussed applies. D sub n times r sub n is bounded by that term with a negative exponent, and it goes to 0.
Another win.
Finally, Case C. The messy case. This is when neither A nor B holds.
This is the nightmare scenario. The sequence isn't growing super fast right now, so it's not Case A, and it's not always growing exponentially, so it's not Case B. It's wobbling. It's unpredictable.
So how do they handle it?
This is where the AI's pathfinding likely really helped. They find that you can still identify local peaks. Not all-time highs, but points that are bigger than their immediate neighbors.
They define a set of these local peaks, script P star, and then they split the tail sum, dq rq, into 2 separate parts, sigma 1 and sigma 2.
It's a pincer movement. Sigma 1 is the near tail, the terms that are close to our current position. Q sigma 2 is the far tail, all the terms far away.
And they show both parts go to 0.
Right. For sigma 1, the near tail, they use the fact that we're at a local peak. So the current term dominates its near neighbors, and a version of lemma 12 can be applied locally to crush it.
And for sigma 2, the far tail.
For the far tail, they use the weaker growth condition, the one with n to the 1 plus tau. They show that even if the growth isn't super fast, it's still fast enough to make the sum of the faraway terms completely negligible.
So the text says, from the splitting, we conclude the limit of dq/rq is 0.
The near part is crushed by the peak property. The far part is crushed by the general growth property. Between the two of them, the whole thing is forced to 0.
Completist check. Did we survive Case C?
We did. We identified the splitting strategy. We saw how they used local peaks. We confirmed that they showed the limit is 0 in all possible cases. Proposition 11 is proven, and therefore Theorem 3 is proven.
Phew. Okay. Part 5. Section 4, Proof of Theorem 5.
Now we switch gears completely. We're done with the irrationality proof. Now we need to prove that if the sequence grows just a little bit slower, related to that key tilde sub W constant, the sum can be rational.
They start with lemma 14, the rational construction.
This is a beautiful piece of math. It's a non-constructive proof that a constructive sequence exists. It uses a nested interval argument.
What does that mean?
Imagine the set of all possible sums you could make with sequences that fit certain rules. The lemma says this set of possible sums creates a union of intervals on the number line. If you want your final sum to be a specific rational number, say 1/2, you need to show that you can choose your sequence terms, a 1, then a 2, then a 3, in such a way that the number 1/2 stays inside the shrinking interval of possibilities at every single step.
Okay, so then the proof of Theorem 5 itself. They define these two sequences, beta sub n and gamma sub n, using the floor function. The latex for beta sub n is beta can L floor C, C in n plus n2 plus 1 R floor.
And phonetically, that's beta sub n equals the floor of capital C times C to the power n plus n squared plus 1.
That n squared in the exponent is interesting.
It is. It adds a slight boost to the growth. It's a technical requirement to make sure the intervals we just talked about are wide enough to always overlap. By choosing these bounds, beta and gamma, carefully based on the root C tilde sub w, they create a lane for our sequence an to live in.
And this lane satisfies the conditions of lemma 14.
Exactly. And lemma 14 then says, okay, since you've built this valid lane, I guarantee there exists a sequence an trapped inside it such that the final infinite sum is a rational number.
It feels like magic. They don't actually give you the sequence of numbers like 2, 5, 12. They just prove that a path through the number line exists that lands exactly on a rational point.
That's the power of this style of argument. It's based on continuity. If you can show that the space of possible outcomes is connected, you can guarantee you can hit any point inside it.
Completeness check. Does this counterexample effectively close the door on improving Theorem 3?
Yes. Theorem 3 says growth greater than x implies irrational. Theorem 5 says growth approximately y implies it could be rational. And since y, which is c tilde sub w, is the best possible lower bound related to the polynomial structure, we know that Theorem 3 is essentially as sharp as it can be. You can't improve it much more using these methods.
Right. Part 6. Acknowledgements and references. The home stretch.
You see who paid the bills.
The third named author is supported by Mid-Career Researcher Program through the National Research Foundation, Korea. That's SANG-HYUN Kim.
Funding matters. It keeps the lights on at the Korea Institute for Advanced Study.
The fourth named author, Croatian Science Foundation for VJEKOSLAV KOVA:C.
Right. And the acknowledgments to people. We thank Thomas Bloom for creating and maintaining the website Erdős Problems.
That website is so important. It digitizes the hundreds of open problems that Erdős left behind, scribbled on napkins and in the margins of letters.
He keeps the legacy alive. And then the big one.
We are thankful to the authors of 10 for building the Aletheia agent and letting the authors use it. Reference 10 is a preprint titled Towards Autonomous Mathematics Research, Preprint 2026.
2026. The paper itself is dated January 30th, 2026. So for us, this is a look into the very near future of how math is done.
If you scan the references, you see Cantor from 1869, Erdős from 1975.
And the AI agents of 2026. This paper is a bridge across 157 years of mathematical thought.
Finally, the affiliations and the emails.
Let's read them.
KB799@cam.ac.uk. That's Kevin Barreto at Cambridge.
Carl011226@gmail.com for JIWON Kang at Seoul National University.
Skim.math@gmail.com for SANG-HYUN Kim at KIES.
KOVA:C at math.HR for VJEKOSLAV KOVA:C at the University of Zagreb.
And SANG-HYUN1555 at stanford.edu for SHENGTONG ZHANG at Stanford.
It's interesting to know JIWON Kang and SANG-HYUN Kim are using Gmail addresses.
A preference for permanence, maybe? Institutional emails can be a pain.
It's a practical choice many academics make.
And that covers the final email address. Have we missed anything?
We have processed the document linearly from the title to the final period. The protocol is satisfied.
So what does this all mean? We just spent all this time deconstructing a single proof about numbers that grow very, very fast.
I think we witnessed a transition. The Erdős-Graham problem was a human problem. It's intuitive, it's elegant. The solution is a cyborg solution.
A hybrid.
It uses the brute force search power of an AI to find the messy but correct path, and then the elegance and deep insight of human mathematicians to refine it, generalize it, and understand its boundaries.
So the AI didn't steal the job of the mathematician?
Not at all. It acted as a new kind of collaborator. It was the scout. It ran into the dark forest of number theory, found a path that no one else had seen, and came back with a rough map. The humans then paved the road and built the city.
And for you, the listener, what's the takeaway?
I think it's about the nature of truth. Whether that truth is found by a silicon brain or a biological one, The fundamental truth of this sum, the sum of 1 over an times an plus 1, remains the same. Under these conditions, it is irrational. It refuses to settle down into a simple fraction.
It is infinite, non-repeating, and
beautiful.
And with that thought, we conclude the unabridged protocol.
QED.
See you on the next deep dive.
Hello and welcome back to the deep dive. Today we are doing something fundamentally different. We're initiating what we're calling the unabridged protocol.
That sounds a little ominous, but I know what you mean. Usually, we synthesize things for you, we summarize, we try to give you the high-level takeaways.
The Blinkist version of a paper, yeah.
Exactly. But sometimes a document just lands on our desk that, well, it refuses to be summarized. It demands a different kind of respect. It demands density.
It really does. We are looking at a paper released, well, in the timeline of the source material on January 31st, 2026. The title is Irrationality of Rapidly Converging Series, a Problem of Erdős and Graham.
And the rule for today is simple.
Line by line.
Symbol by symbol.
No skimming, no jumping ahead.
We are going to respect the mathematics. We're starting right at the top of page 1, and we are not stopping until we hit the very final email address on the very last page. We have the time, and we have the mandate.
And just to keep us honest, after every single logical segment, a paragraph, a proof, maybe just a complex definition, we are going to pause. We'll do a completeness check.
Right. We have to look each other in the eye, metaphorically speaking, and agree that we haven't left any nuance on the table before we move to the next line.
I'm ready. This paper it's a beast, but it's a beautiful one. It involves number theory, the golden ratio, and a very specific and historic collaboration
between humans and artificial intelligence.
Specifically, Google DeepMind's Gemini DeepThink and an agent called Alethea. We're going to get into the philosophy of that later on for sure. But first, the text.
The text itself.
Top of page 1, the title. Irrationality of Rapidly Converging Series, a Problem of Erdős and Graham. Let's unpack that before we even look at the authors. The first word, irrationality.
Right. Let's stop there.
Right.
We have to establish the playground we're in. So in the world of numbers, you have the rationals. These are the comfortable numbers.
The ones we all know.
The ones we all know. Fractions, 1/2, 3/4, even something like 100 over 3. Any number you can write as an integer p over another integer q, as long as q isn't 0.
And their decimal expansions are predictable.
Totally predictable. They either stop, like 0.5, or they repeat forever, like 0.333, and so on.
And then there are the irrationals.
The wild ones, pi, the square root of 2. You absolutely cannot write them as a simple fraction. They're decimal expansions, they go on for infinity, and they never, ever settle into a repeating pattern.
And proving a number is irrational is notoriously hard.
Though it's incredibly difficult because you're proving a negative. You have to prove that no pair of integers exists in the entire infinite universe of integers that can represent your number. It requires a completely different toolkit than just proving something exists.
Okay, so that's irrationality. The second part of the title, rapidly converging series.
Right, so a series is just a sum of a sequence of numbers, 1 plus 1/2 plus 1/4 plus 1/8, on and on. Convergence just means that the sum doesn't explode to infinity. It actually settles down on a finite value. That sum I just mentioned settles on too.
But the key phrase here is rapidly converging.
That's the operational phrase. It means the terms you are adding get tiny very, very fast.
Can you give me an analogy for rapidly? I mean, how fast is fast?
Okay, sure. Imagine you're walking toward a wall that's, say, 2 meters away. A normal converging series is like taking a step of 1 meter, then a step of 1/2 meter, then a 1/4 meter. You get there eventually.
Flint-Nose paradox.
Kind of, yeah. Now, a rapidly converging series is like taking a step of 1 meter. Then the next step is millimeter. And the next step is the size of an atom. And the next one is the size of a quark.
So astronomically fast shrinking.
The terms just vanish so quickly that the sum is incredibly thin, you could say. And in number theory, this thinness is a clue. If a series converges fast enough, the final sum is almost forced to be irrational.
Why is that?
Because there simply isn't enough slop in the numbers to form a repeating rational pattern. The value gets pinned down too precisely, too quickly, for the clumsiness of a repeating decimal to ever catch up.
That's a great way to put it. Okay, and finally, the last part of the title, a problem of Erdős and Graham.
Paul Erdős and Ronald Graham. I mean, these are the Lennon and McCartney of 20th century mathematics.
That's a big claim.
It is, but it's true. Erdős was this wandering genius, the most prolific mathematician in history. Graham was a giant in combinatorics. They wrote this seminal book back in 1980, posing hundreds of open problems.
And if their names are on a problem.
It's a classic. It's a benchmark. Solving one of their problems is like pulling a sword from a stone. It's a significant event.
Okay, so let's see who pulled the sword. The author list. We have 5 names here. Kevin BARRETO, JIWON Kang, SANG-HYUN Kim, VJEKOSLAV KOVAʼC, and SHENGTONG Zhang.
A truly international team. And we'll see later in the affiliations, they span Cambridge, Seoul, Zagreb, Stanford. It's a global effort.
But note, there are 5 human names listed.
An important distinction. The AI isn't listed as an author. It's treated as a tool, or maybe a collaborator that doesn't get a byline. And that's the tension, a philosophical point we are definitely going to explore as we get into the AI declaration section.
All right, completeness check. We've analyzed the title, Irrationality, Rapid Convergence, the historical weight of Erdős and Graham, and we've noted the authors. Are we ready for the abstract?
I believe so, yes. We have the context. We know what the words mean. Let's see what they did with them.
Moving to the abstract. This is, of course, the summary of the paper, but per our protocol today, we are going sentence by sentence. Sentence 1. Answering the question of Erdős and Graham, we show that the double exponential growth condition. And here we hit our first piece of mathematics.
Okay, let's read this out loud precisely because this is going to be important. So the condition is given in LaTeX as lim sub 2 in 50.
Okay.
And the way we would vocalize that for you and for the TTS is the limit supremum as n approaches infinity of a sub n to the power of 1 over phi to the n equals infinity.
All right, let's break that down. Limit supremum. How is that different from just a regular limit?
Good question. A normal limit implies that a sequence settles down to a single specific value. A limit supremum, or lim sup, is a bit looser. It looks at the upper boundary, the ceiling of the sequence, as it goes to infinity.
So it doesn't have to settle down.
Exactly. The sequence can fluctuate, it can go up and down, as long as its peaks keep getting higher and higher, heading towards infinity. It's a more robust condition.
And this is being applied to the abstract defines this immediately as for a monotonically increasing sequence of positive integers.
So we have a list of integers, and they're always getting bigger, 1, 5, 20, 100, whatever they may be. And the condition is looking at a root of that number n.
But it's a very weird root.
It's a very weird root. The root of order fin phi to the n.
In the abstract notes right away. Here, fin phi denotes the golden ratio, 1 plus 2.
Which is, approximately 1.618. And this is the first real surprise of the paper. You expect to see the golden ratio in, geometry or pine cones or classical architecture.
Not in number theory about rational numbers.
Yeah. But it appears because it governs the recursive nature of how these terms in the series need to interact to guarantee irrationality.
Yeah.
It's the magic number for this kind of problem.
The sentence continues. Together with the bound in an plus 1, an 1 plus tau.
Let's vocalize that.
Yeah.
A sub n times a sub n plus 1 is greater than or equal to n to the power of 1 plus tau.
Is sufficient for the series sum n plus 1.
Which reads as the sum from n equals 1 to infinity of 1 over a sub n times a sub n plus 1.
To have an irrational sum. And it specifies that tau 0 tau is greater than 0.
Okay, so let's try to rephrase that whole claim in plain English. If you have a sequence of integers and that grows super, super fast, specifically, a growth rate governed by this golden ratio, double exponential. And if the product of any two consecutive terms grows at least a little bit faster than n, then the sum you get by adding up 1, and an plus 1, is guaranteed to be an irrational number.
And that answers the original question from 1980.
That's the answer, yes.
You mentioned double exponential. What does that mean in simple terms?
Right, so exponential growth is what we're all familiar with, 2, 4, 8, 16, 32. It gets big fast, right?
Right.
Double exponential growth is, well, it's growth on steroids. It's 2, then 4, then 16, then 256, then 65,536. And the next number has nearly 20,000 digits.
So incomprehensibly fast.
It's explosive. And the paper is saying you need this explosive level of growth in your sequence to guarantee the sum is irrational. If it grows any slower, you might accidentally land on a rational number.
Okay, that's sentence 1. Sentence 2 of the abstract. We also provide a positive generalization to, and here's a more complicated looking sum.
It is, but it's a logical next step. The latex is sum interbound, CD's an plus d1 dc d1.
And the vocalization.
That would be the sum from n equals 1 to infinity of 1 over the product of a sub n to the w naught through a sub n plus d minus 1 to the w sub d minus 1.
Wow, that is a mouthful. What's it doing?
It's the generalization. The original Erdős problem was just about pairs, 1 and an plus 1. This new version looks at a product of d consecutive terms, and each of those terms can be raised to a specific power, w.
So they're not just solving the original problem.
No, they're solving the whole class of problems. They took the original question and said, what if we use triplets instead of pairs? What if we square some terms but not others? What if we mix and match? And they solved it for all of those cases.
Sentence 3, and a negative result showing that some of its instances are essentially optimal.
Negative result always sounds bad, but in math, it's actually fantastic news.
How so?
It means we found the edge. They proved that if you relax their growth condition, if you grow any slower than what they require, then the theorem breaks. You can find a sequence where the sum is rational.
So it means their theorem is sharp.
Perfectly sharp.
Yeah.
You can't tighten the screws any further. It defines the exact boundary between the rational and irrational worlds for these types of series.
And now for the final sentence of the abstract, which for many people is the real headline.
This is the big one.
The original problem was autonomously solved by the AI agent Alethea, powered by Gemini DeepThink, while the remaining material is largely a product of human-AI interactions.
Autonomously solved. I mean, that is a historic phrase to see in a mathematical abstract. It doesn't say the AI helped us calculate something or the AI found a pattern. It says the AI solved it. The machine cracked the nut, and then the humans came in and helped build the tree around it.
Okay. Completeness check. We've defined all the key terms from the abstract: irrationality, convergence, the golden ratio, double exponential growth. We've unpacked the positive generalization and the negative result, and we've touched on the nature of the human-AI collaboration. Are we satisfied with our understanding of the abstract?
I think so. We've established the what and the who. Now we need to dig into the how. Let's move to section 1.
Section 1, and the title is Declaration of AI Usage. This is interesting placement. Usually you'd see something like this in a footnote or maybe an appendix.
Right. Putting it up front as section 1, that's a statement. It signals that the methodology here is just as important as the mathematical result. They're showing their work not just the math, but the cognitive process that generated the math.
The first paragraph just confirms this resolves the problem from Erdős and Graham's 1980 book. It notes that this has been an open problem for 46 years, from 1980 to 2026.
And then they give us this numbered list, a timeline from 1 to 6. This is essentially the biography of the proof. We need to go through these points one by one to really understand the workflow.
Okay, point 1, the origin. Erdős and Graham post question 1 below in their well-known 1980 problem book, expressing the belief that it should be solvable, perhaps by standard tools, and that some generalization should exist.
That phrase, perhaps by standard tools, it almost sounds like a taunt from the grave, doesn't it?
It does. What do you think that implies?
Well, it's a classic mathematician's understatement. Erdős likely thought, look, we don't need to invent new physics or a whole new branch of calculus for this. There's just a clever trick, a clever application of existing methods that we haven't seen yet.
But it took 46 years.
Exactly. The fact that it sat unsolved for nearly half a century suggests that those standard tools were maybe heavier than they looked, or they needed to be applied with a level of precision and brute force insight that humans just struggle to find on their own.
Point 2. Enter the machine. Alethea, a custom math research agent built on top of Gemini DeepThink, whose development was led by Tony Feng, found a solution to question 1.
Aletheia. It's a Greek word. It means truth or disclosure, a very fitting name for an agent designed to reveal proofs.
The text then adds a fascinating detail. From the original output, it was clear that some generalization was possible. Specifically, the proof used rough estimates such as 1.7 to 1.7 is less than 2, log x is less than x, etc.
This part is just, it's amazing. The AI didn't produce a perfect, polished, elegant crystal of a proof. It used rough estimates. It basically said, look, 1.7 is less than 2, and that gives me enough wiggle room to make the argument work. That is an incredibly human way of thinking.
It's intuition.
It's a form of intuition, yes. You prioritize getting to the answer over formal elegance. It hacked its way through the jungle first to prove a path existed. This completely contradicts the popular idea that computers can only do exact, formal, step-by-step logic. Here, the AI used approximation to find a path to truth.
Point 3. The authors realized and proved that one can relax the original growth condition and generalize the series. This generalization is now formulated as part 1 of Theorem 2.
This is the handoff. The AI provides this messy but correct proof for the specific case. The humans look at the AI's logic and say, wait a minute, the core idea here holds even if we stretch the numbers. We can clean this up, formalize it, and make it apply to a much broader class of series.
So they formulate Theorem 2 based on the AI's initial breakthrough.
But then look at point 4. The ball gets passed back. Gemini DeepThink discovered a further generalization among many plausible variations of the hypotheses, and then, jointly with Alethea, proved it. This generalization corresponds to Theorem 3.
So the humans generalize the AI's work to create Theorem 2, and the AI looks at the human generalization and says, that's good, but I can do better. It finds an even more general result, Theorem 3. It's a ping-pong match.
AI to human to AI. Exactly. And that phrase, jointly with Alethea, suggests that Gemini DeepThink, maybe the core reasoning engine, formulated the idea, and Alethea, the proof-checking agent, verified all the steps.
Point 5. The authors found counterexamples that tightly complement the previously mentioned result. These are discussed in Part 2 of Theorem 2.
Now, the humans are playing the role of skeptic. The AI seems to be brilliant at proving things are true. The humans are bringing the crucial skill of asking, okay, but where does it stop being true?
The negative result again.
That's the negative result. Finding the boundary of a theorem, constructing a specific scenario that breaks the rule, is often just as hard as proving the theorem itself. It requires a different kind of creativity.
And finally, point 6. Finally, inspired by Erdős' paper 4, the authors were able to weaken the hypotheses further to obtain Theorem 3 below. Also, a more general negative result was found and formulated as Theorem 5.
So the final published paper is this beautiful blend. It started with an AI discovery, which was refined by humans, which was then generalized further by the AI, which was then bounded by human skepticism, and then the whole thing was polished by the humans looking back at old papers from Erdős himself. It's a collaboration across time and, well, across species in a way.
The closing paragraph of this section is really vital. It says, this work also represents an interesting use case for AI in that it originated when Alethea searched over a large set of open problems and autonomously narrowed them down to those it could solve.
I mean, that's the scary and cool part right there. The AI wasn't fed this problem. It went hunting. It scanned the mathematical literature, found the Erdős-Graham book, looked at the problems inside, and decided for itself, I can probably take that one, but not this one. That's strategic autonomy. It's evaluating its own capabilities against the difficulty of unsolved problems.
But they do add a disclaimer. However, we emphasize that the writing of the paper was entirely done by the human authors.
A crucial distinction for right now. The ideas in the paper are a hybrid, but the prose you're reading is human. We are reading human words that are describing machine thoughts. This highlights the current state of AI. It can reason, it can discover, but it still relies on us to communicate those discoveries effectively to the scientific community.
Okay, that's section 1, completeness check. We covered the full timeline of the discovery, the specific roles of Alethea and the human authors, AI as solver and generalizer, humans as refiner, skeptic, and writer. Did we miss anything in that declaration?
I think we've unpacked it thoroughly. The workflow is clear. Let's move on to the actual mathematics in section 2.
Section 2, introduction. It begins on page 2, and they state the question formally. Question 1. Is it true that if a 1A2 dot a sub 1 is less than a sub 2 is less than ... is a sequence of positive integers with? And here's the original condition.
Let's read it. The latex is limit 50 and 12(1).
And vocalized.
The limit infimum as L(n) approaches infinity of a sub n to the power of 1 over 2 to the n is greater than 1.
Okay, let's compare this to the abstract. The abstract had limit supremum and the golden ratio. This original question has limit infimum and the number 2.
Right, so 2n is a clear double exponential growth rate, 2, 4, 8, 16. The condition in 12(1) means that in the long run, an n has to grow at least as fast as something like C2, where C is just a constant slightly bigger than 1.
And the question is, if you have that specific double exponential growth, is the sum 1, an am plus 1, sum of 1 over a sub n times a sub n plus 1 necessarily irrational?
That's the question, and the paper immediately confirms. The present paper provides a positive answer to question 1 and its natural generalizations, namely theorems 2 and 3.
So the answer is simply yes.
Yes.
The paper then provides some historical context. It says, the proposers of question 1, Erdős and Graham, noted that hypothesis 2.1 should be enough to imply the conclusion.
And there's that phrase again, should be enough. They had the intuition, but they also remarked that it was easier to show if the growth was much faster, if the limit was infinity, not just greater than 1. The nuance here is the gap between the limit equals infinity, which is a very strong growth condition, and the limit infimum is greater than 1, which is consistently strong, but not necessarily infinite growth. This paper closed that technical gap.
Okay, now the paper makes a distinction between Ahmes series and Cantor series, which I found interesting. Series of the forms sum of 1 over a sub n are sometimes called Ahmes series.
Right. Ahmes was an ancient Egyptian scribe. He wrote the Rhind papyrus. The Egyptians famously didn't use fractions like we do, like 34. They expressed everything as sums of unit fractions, like 12 plus 14. So sums of unit fractions are named in his honor. It's one of the oldest concepts in written mathematics.
On the other hand, series of the form sum1 bn, a1, a2, c dots are known as Cantor series.
Let's read that math. Sum of d sub n over the product of a1 through an.
And that's different how?
The denominator is a running product of all the previous terms in the sequence. This creates a very specific, rigid structure. The problem in this paper, 1 and an plus 1, deals with something in between these two classical forms.
Oh, so?
Well, it's not fully Ahmes because there's a product in the denominator, but it's not fully Cantor because the product only involves two adjacent terms, not the entire history of the sequence. It's a hybrid structure, which is part of what made it a unique and challenging problem.
Okay, let's get to the real meat. Theorem 2. This is the generalization the humans made.
Yeah.
Theorem 2. Fix a positive integer d. Let psi 1 psi is greater than 1 here be the unique positive solution to 2. Psi this 1 plus 1 psi to the d equals psi to the d minus 1 plus 1.
Okay, stop right there. That equation, psid1 plus 1, is the heart of the generalization. It's a characteristic equation that defines the magic growth constant for a product of d terms.
So this CI changes depending on d.
Exactly. If d2, which is pairs of numbers like in the original problem, the equation becomes pa2 equals pi plus 1.
That's the equation for the golden ratio.
It is the exact defining equation of the golden ratio. So for the original problem, pi is phi. If you were looking at triplets d3, you'd get a different number, sometimes called the Fibonacci constant. This one equation tells you precisely how fast your sequence needs to grow to guarantee irrationality for a product of d terms.
Part 1 of Theorem 2 states, if a monotonically increasing sequence satisfies lim d and when ps1,
which is limit of the sub n to the 1 over psi to the n equals infinity.
Then the sum from n1 to infinity of 1 and am plus 1 plus d minus 1 is an irrational number.
Let's read that sum. 1 over the product of a sub n through a sub n plus d minus 1. So there you have it. That's the generalization. Instead of just pairs, they solve it for the product of any number d of consecutive terms, and the required growth rate is governed by that special constant ps.
And part 2 is the counterexample. For every constant c in the interval 1 to infinity, there exists a strictly increasing sequence. Satisfying limit equals c such that the infinite sum is a rational number.
And this is the gap we talked about. If your sequence grows at an infinite speed relative to this Beeson rate, part 1, you are safe. The sum is irrational. But if it only grows at a constant speed c relative to that rate, part 2, you fall off the cliff. You might land on a rational number.
So the boundary is literally at infinity.
Exactly. You need that truly super fast, ever-accelerating growth to escape the gravitational pull of the rational numbers.
Okay, that brings us to Theorem 3. The paper calls this the master generalization, and this is the one formulated by the AI.
Yes, after seeing the human's theorem 2.
Theorem 3. Fix a positive integer d and a tuple of non-negative integers, w0, we, w1, docs, wd1.
Such that wd1 of 1.
These are the weights. Now, we're not just multiplying terms together, we're raising them to powers. So you could have a term like an a squared times am plus 1 to the 5th power. The vector w just tells you what all the powers are.
WDL dots, wd-1, that it defines this polynomial.
Yeah, this looks a bit scary at first, but it's the core of the AI's insight. The latex is Pw of x tools 1 from some j, yz1, wj, xj, wx2.
And we read that as P sub w of x is defined as x minus 1 times the sum from j equals 0 to d minus 1 of wjx to the j minus w times x to the d minus 1.
What on earth is that polynomial doing?
It's beautiful, really. The algebra of this polynomial perfectly captures the geometry of how the terms in the series overlap and interact. The root of this polynomial, which the paper calls KOVAʼ, is the new magic constant.
So the golden ratio was just a special case.
It was just a special case of this polynomial for the simple case where DO2 and the weights are 1, 1. This theorem unifies everything. It says that for any combination of powers you can dream up, there is a specific polynomial, and its unique positive root dictates the growth rate you need for irrationality. It's an incredible generalization.
So the theorem then states that if some other conditions hold, and importantly, the growth condition lim sup to an elephany holds,
limit supreme of a sub n to the 1 over cw to the n equals infinity?
then the generalized sum is irrational.
Yes. This theorem covers every possible variation of products of powers of consecutive terms, is the comprehensive final answer.
And remark 4 just briefly explains that this polynomial PWX is guaranteed to have a unique positive solution greater than 1, using something called Descartes' rule of signs.
Right, that's just a standard bit of polynomial calculus to reassure us that the constant q is always a well-defined real number greater than 1. We're not chasing imaginary roots or anything strange here.
Okay. Then we have theorem 5, the negative counterpart. It defines the slightly different polynomial, tilde eject,
The latex is tilde j xj xd1.
which we read as p tilde sub w of x equals x minus 1 times the sum of wjx to the j minus x to the d minus 1. What's the difference?
It's subtle but crucial. In the first polynomial, the last term was negus wxd1, where w was the maximum weight. In this new one, it's just negus xd1, which is equivalent to saying the maximum weight is 1.
And this weaker polynomial defines a smaller root, tilde q.
Correct. And theorem 5 says that if your sequence only grows as fast as this smaller constant tilde q, then you can construct a case where the sum is rational.
So there's a gap of mystery between the constant sodio from theorem 3, which guarantees irrationality, and the smaller constant tilde from theorem 5, which allows for irrationality.
Exactly. Theorem 3 says, grow faster than Clo, you're irrational. Theorem 5 says, grow like tilde q, you might be rational. There's a zone in between where the behavior might still be open for some very complex weight combinations. But for most simple cases, these theorems bracket the behavior perfectly.
And they make this concrete with example 7 on page 5. They say when w equals 1, 0, 2, 1.
So that corresponds to a denominator that looks like an a core to the power of 1 times an plus 1 to the power of 0 times an plus 2 squared times an plus 3 to the power of 1, or more simply 1 and an plus 2 to an plus 3.
For that specific case, they calculate the root C area is approximately 1.914, while the root from the negative counterpart, tilde q, is about 1.345.
So there are the hard numbers. If your sequence in an A grows with a base of 1.914 in that double exponential way, the sum is guaranteed to be irrational. If it only grows with a base of 1.345, it could be rational. It turns the abstract theory into a calculator-ready test.
Okay, completeness check for section 2. We've gone through the original question 1, theorem 2, the human generalization, theorem 3, the AI's master generalization, theorem 5, the negative counterpart, and the polynomials that define the critical growth rates. Have we got the whole map?
I think we have the map. We understand the landscape of the results. Now we have to drive the car through the proof. Section 3.
Section 3, proof of theorem 3. This is the long haul, from page 5 to 11. It starts by saying, we utilize a classical irrationality criterion that dates back to at least Fourier's proof of the irrationality of the number E.
And this is presented as lemma 8. It's often attributed to Kurt Mahler, who was a giant in a field called Diophantine approximation.
Let's unpack lemma 8. Let be non-negative rational numbers such that S some z indiffides.
Let's read that. S is defined as the sum of z sub n, and it's less than infinity. So basically, we have a convergent series where every term we are adding is a rational number.
And Dn be positive integers such that Bn sum 1 he is an integer for every n.
And that's a d sub n times the sum of z sub n from n equals 1 to n. This dn is just a common denominator for the first n terms of the series. If you add up the first n fractions and multiply by their common denominator, you get an integer. This is just how fractions work.
The core of the lemma states, if S is rational, then lamin nzn 0.
Okay, let's break that down. The latex is limit infimum as n approaches infinity of d sub n times the quantity s minus the partial sum is greater than 0.
It seems complicated.
Let's do an ELI 5. Explain, like, I'm 5, but for, math nerds.
Perfect.
Assume your total sum s is a rational number. Let's say it's BQ. The partial sum, the sum of the first n terms, is also a rational number. The difference between the total sum and the partial sum is the tail, all the stuff you haven't added yet.
S minus the partial sum is the tail.
Okay. Mahler's criterion says, if you multiply that tail by the common denominator dn, and if the total sum s was rational, then for large n, that result must be an integer. And since the tail is positive, that integer has to be at least 1.
So the value of dn times the tail can't get arbitrarily close to 0. It has a floor. It can't go below 1.
It has a floor at 1. It is stuck being 1 or 2 or 3 or some other integer. It cannot be 0.5 or 0.1 or 0.00001.
And so the strategy of the proof is...
proof by contradiction. The authors are going to prove that for their series, the value of dn times the tail does go to 0. It crashes right through that floor.
And if it goes to 0?
If it goes to 0, Mahler's condition is violated. If Mahler's condition is violated, the initial assumption that the sum s was rational must be false. Therefore, S must be irrational. QED.
That is a beautiful logical trap. The entire proof comes down to one goal.
The whole game is, make dn times the tail go to 0. Catch the 0.
Okay, next up is lemma 9. The paper calls it the Borel-Erdős trick. If delta non are positive sequences, and lim sup's in50, then the set P is infinite.
Let's read that set definition. Key m ohm plus 1, or the set P of integers m, such that mom plus 1 is greater than 1 plus delta m times the max of all previous mom.
What's this doing?
This is about finding peak indices. The condition lim sub mum in FD means the sequence mun goes to infinity. It can't just meander upwards. There must be infinitely many moments where the next term, mum plus 1, is not just bigger than what came before, but decisively bigger, a new record holder by a certain margin. The set P is the infinite set of these record-breaking indices. The proof will rely on analyzing what happens at these specific peak moments because that's where the growth is most dramatic and easiest to control.
We don't need the condition to hold everywhere, just at these peaks.
Exactly.
And lemma 10, dyadic blocks and estimates. This introduces Vinogradov notation, the double less than sign.
Right. Fx, f of x is double less than g of x. It's just standard shorthand in analytic number theory. It means f is bounded by g times some constant. F is essentially smaller than g, ignoring constant multipliers.
And lemma 10 gives two technical estimates for a certain sum. Part 1 says if the denominator xk grows polynomially, the sum decays polynomially. Part 2 says if xk grows exponentially, the sum decays almost exponentially.
These are just the technical tools they'll need later. They're pre-calculating the decay rates of the series tail under different growth conditions. We'll see them get plugged in when they prove the main proposition.
All right, completeness check on the lemmas. We have the logical framework from Mahler's criterion, the tool for finding peak indices from the Borel-Erdős trick, and the technical estimates from lemma 10. We have our toolkit.
Now let's see how they use it. We're on page 7, the setup for the proof of theorem 3.
They start by defining mun log n we n equals log a n over c to the n. This is equation 3.2.
And here c is that special constant c2 from the polynomial. This mun is the key quantity. The assumption of the theorem that lim sup a 1 in FD is the same as saying lim sup in FD. So we can now use the Borel-Erdős trick on this mun.
They also define xn in equation 3.4 xn and plus 1w at xsj and t1.
Xn defined as the product of a sub n minus d plus 1 to the w naught, all the way to a sub n to the w d minus 1. This is just a formal name for the denominator, the nth term in our series.
And dn in equation 3.8, dn, proc k1n akw.
dn defined as the product from k equals 1 to n of ak to the w. And this is the common denominator we need for Mahler's criterion. It's the product of all the x up to n, each raised to the maximum weight w.
Okay, all the pieces are on the board. Then comes the main target, proposition 11.
This is it. This is the whole proof in one line.
The statement is, limit FD dn Rn equals 0, limit infimum of dn times Rn equals 0, where Rn is the tail of the series.
This is the goal. As we discussed, if they can prove proposition 11, they show that dn times the tail goes to 0. This violates Mahler's criterion, which forces the sum to be irrational. So the entire 11-page proof boils down to proving this one proposition.
And they prove it by splitting the problem into 3 mutually exclusive cases.
Divide and conquer, the method of exhaustion.
Case A. There are infinitely many indices n where the next term is huge compared to the accumulated denominator. The condition is xn plus 1 dnm.
This is the super fast growth case.
Yeah.
If the sequence has these massive, unpredictable jumps, then the tail of the series right after such a jump is incredibly tiny. They apply lemma 10, part 1, and show easily that dnRn gets squashed down to 0. So case A is solved. The sequence grows so fast it immediately crushes any possibility of being rational.
Case B. The sequence doesn't have those massive jumps, but it has steady, strong exponential growth. The condition is Ahmesian.
This is the steady exponential growth case. Here they use the more subtle lemma 12 about local peaks, and this is where the magic of that polynomial P comes in. The constant SHENGTONG was constructed specifically to make the inequalities in lemma 12 work out perfectly. They use it to show that the logarithm of dnRn goes to negative infinity.
And if the log goes to minus infinity, the value itself goes to 0.
Exactly. So case B is solved.
That leaves case C. Neither A nor B holds.
This is the slow and weird growth case. This is the hardest one. It means the sequence doesn't have those huge jumps, and it also doesn't grow steadily like an exponential. It can stumble, grow slowly for a while, then speed up a bit.
So how do they handle that?
It's a much more delicate argument. They have to use an iterative process. They use the Borel-Erdős trick to find those peak indices we talked about. They then split the tail of the series into 2 chunks. a near tail and a far tail.
Sigma 1 and sigma 2.
Right. They show that the near tail, sigma 1, is small because it happens right after a peak where the growth is locally strong. They use the estimates from lemma 10 and 12 for that. Then they show the far tail, sigma 2, is also small just because it's so far out that all its terms are tiny.
And since both parts of the tail go to 0, the whole tail goes to 0.
Exactly. They put it all together and conclude limit dq_rq=1. And that proves proposition 11.
And proposition 11 proves theorem 3.
The trap is sprung. Mahler's criterion is violated. The number must be irrational.
There's a quick remark 13 that follows, which just tightens up some of the logic about how far apart those peak indices need to be.
Yeah, it's a technical point. Just make sure all the estimates are rigorous.
Completeness check for section 3. We've walked through the overall strategy using Mahler's criterion and the 3 cases they use to prove proposition 11, the super fast case, the exponential case, and the slow mixed case. We've covered the proof.
We have. It's a classic proof by exhaustion. No matter how the sequence behaves, whether it sprints, runs, or stumbles, as long as it satisfies that initial high-level growth condition, the tail of the series vanishes relative to the denominator. The logic is sound.
Excellent. That brings us to section 4. Proof of theorem 5. This is on pages 12 to 14. This is the negative result, the counterexample. They have to actually construct a sequence that makes the sum rational.
Right. The goal shifts completely. Before we were proving something must be true for all sequences.
Yeah.
Now we just need to build one sequence that breaks the rule.
Yeah. It starts with lemma 14, the construction. They define 2 sequences, Batan and Gammon, and want to pick their sequence n from the interval between them.
They're setting up a series of nested choices. For each n, they want to pick an integer and within a specific range, Batan, Gammon, and the goal is to steer the final sum toward a rational number.
The proof uses a clever finite union of intervals argument. I'm looking at equations 4.5 through 4.8.
Yes, this is the core idea. Think of it like this. At each step n, the possible values of the partial sum, depending on your choice of the next term, an plus 1, form a collection of little intervals. The key question is, do these intervals have gaps between them, or do they overlap?
And they show they overlap.
They show they overlap. The inequality in 4.8 shows that the left endpoint of one possible interval is less than or equal to the right endpoint of the next one. This means there are no gaps. You can form a continuous range of possible sums.
And if you have a continuous range,
you can steer the sum to hit any value you want within that range. And since there are infinitely many rational numbers, you can definitely steer it to land on one of them. The lemma proves that this steering is possible.
Then comes the execution of theorem 5 proof. They define the specific sequences for Batan and Gammon using the floor function and the slower growth constant tilde.
They build the highway, basically. They define the boundaries of the road.
They invoke lemma 14 to show that the road has no potholes,
no gaps,
and therefore they can construct a sequence in of them that drives the sum to a rational number.
Exactly. They do mention a minor detail, that their construction might not be strictly increasing at the very beginning, but they say you could just redefine the first few terms by hand to fix that, which doesn't affect the infinite sum.
And that proves theorem 5. It shows that the slower growth rate really is slow enough to allow for rationality, confirming that the result in theorem 3 is sharp. Completeness check for section 4. We've covered the goal construction, the tool, lemma 14's interval overlapping argument, and the execution. Are we clear on the negative result?
I think so. It's a constructive proof, very different in feel from the previous section, but the logic is clear.
Okay, section 5, the back matter, page 14. First, the acknowledgments.
And they are very specific, which is good academic practice. They list grant numbers. The third named author is supported by Mid-Career Researcher Program from NRF Korea. The fourth named author, Croatian Science Foundation, FANBAP.
They also thank 2 specific people. We thank Thomas Bloom for the Erdős Problems website and Terence Tao for valuable comments.
And seeing Kerry Tao's name, even just for valuable comments, is always a seal of quality. He's arguably the greatest living mathematician. His involvement suggests this is top-tier work.
And then, the crucial line for our story, we are thankful to the authors of 10 for building the Aletheia agent.
Acknowledging the tool makers.
Then we hit the references. It's a list of 10 sources. It's interesting to see the time span. We have reference 2, Cantor from 1869.
The very origins of this kind of thinking about series.
And then we have reference 6, the Erdős and Graham book from 1980, and it ends with reference 10, Feng T. Trin, TH, towards autonomous mathematics research, preprint 2026.
And look at that author list for reference 10. It's huge. That's the Google DeepMind team. That paper, Towards Autonomous Mathematics Research, is likely the manifesto for this new era of AI-driven mathematics.
The final part of the paper, author affiliations. BARRETO from Cambridge, Kang from Seoul National University, Kim from KAS in Korea, KOVAŞ from the University of Zagreb, and ZHANG from Stanford.
Truly a global collaboration.
And the final piece of text in the entire document is an email address, SEH1555@stanford.edu, and that concludes the document.
We have reached the end. The unabridged protocol is complete.
So, final debrief. Did we miss anything? Did we leave any stone unturned?
I don't think so. From the definition of a lemma to the dyadic block estimates in lemma 10 to the interval construction in lemma 14, we have respected the density.
So this paper answers a question from 1980, but in a way, it also answers a question from 2026. Can AI do real creative mathematics? And the answer seems to be a very complicated yes.
It's a yes, but it's a collaborative yes. The workflow was. AI solves, humans generalize, AI generalizes further, humans find the boundaries and perfect the presentation. It's a loop.
You called it Centaur mathematics before we started. Half human, half machine.
It really is. The distinction between the authors starts to blur. The ideas in this paper flowed between Aletheia and the human team so fluidly that Theorem 3, the master theorem, is explicitly listed as an AI discovery. That's a new frontier.
Which leads us to our final provocative thought for you to take away. If AI can find rough proofs that humans refine, and humans find generalizations that AI then refines, are we approaching a point where the author of a mathematical paper is just the editor of an AI's thought process?
Or perhaps it's the other way around. The AI is the editor of ours. It scanned all the open problems, it selected the one that was right for solving, it found the core insight, and it guided its human collaborators to the sharpest possible version of the truth. Maybe the name Aletheia, the Truth, was the most fitting name they could have possibly chosen.
On that note, thank you for joining us on this deep dive. We'll see you on the next one. Welcome back to The Deep Dive. Today is Saturday, January 31st, 2026.
And that's a date you might want to remember. Because less than 24 hours ago, something pretty remarkable happened. A paper dropped.
A paper that, and I don't think this is an exaggeration, could fundamentally alter our understanding of how mathematics is done.
For sure. We're talking about the collaboration between human mathematicians and, well, artificial intelligence to solve problems that have been sitting on the shelf for decades.
The paper is titled Irrationality of Rapidly Converging Series, a Problem of Erdős and Graham. It appeared online yesterday. And, normally this is the point where I'd say we're going to distill it for you, give you the highlights, the summary.
Like the cocktail party version.
Exactly. But we can't do that today. It just wouldn't be right.
No, not for this one.
Given the nature of this paper, and specifically because of who solved the central problem, or maybe I should say what solved it, our usual approach just isn't going to cut it.
So we're doing something different.
Yes. Today, we are activating the unabridged protocol.
The unabridged protocol. Okay, for anyone new to what that means, it's a complete shift in how we do things. We are throwing the idea of a summary right out the window.
No skimming. No skipping ahead to the good part.
We're not glossing over the technical lemmas or the boring bits.
Yeah.
We're going to read and analyze this document, this paper, in a completely linear fashion.
From the title page all the way to the very last author affiliation and email address.
We're basically operating under the assumption that you, our listener, have all the time in the world. We're going to pause. We're going to dig in. At every definition, every single formula, every logical step, we're going to stop.
And we're going to make sure that we haven't just, heard the words, but that we've actually understood the meaning behind them.
It's the only way. I mean, with a proof like this, a proof about irrationality, precision is everything. If you skip a single step, a single inequality, the whole logical chain just falls apart.
And a broken chain proves nothing.
Nothing at all.
So get comfortable. This is not a background listening. We have a huge amount of ground to cover. And we're going to start at the only logical place, the very beginning.
Part 1. The title and the abstract.
Let's just read the title out. Irrationality of Rapidly Converging Series, a Problem of Erdős and Graham.
Okay, stop right there. 3 words in, and we already have to unpack something. Irrationality.
Right. In everyday language, irrational means something that doesn't make sense, something unreasonable. But here, In number theory, it has a very, very specific meaning.
A very precise one.
Hmm.
An irrational number is a real number that you simply cannot write as a ratio of two integers. You can't express it as a simple fraction, like p divided by q.
The classic examples everyone learns in school are numbers like pi or the square root of 2.
Exactly. And if you try to write them out as a decimal, they go on forever. And not just forever, but forever without ever repeating a pattern. It's infinite, non-periodic chaos, in a way.
So this paper is on a hunt for that kind of number. It's trying to prove that if you add up an infinite number of things in a specific way, the final result is one of these strange non-fractional numbers.
Precisely. Which brings us to the next part of the title. Rapidly converging series.
A series is just adding up a list of numbers, right? A sequence.
Right. Term 1 plus term 2 plus term 3 and so on, forever. Now, for that sum to not just explode to infinity, for it to actually settle down to a finite number, which we call converging, the terms you're adding have to get smaller and smaller.
But the title doesn't just say converging, it says rapidly converging.
And that's the key. It's not enough for the terms to just get small. They have to get small, well, incredibly fast. In this field, the faster the terms shrink towards zero, the easier it generally is to prove something about the sum's irrationality.
Why is that?
Because the tail of the sum, all the infinite stuff you haven't added yet, becomes so insignificant so quickly that you can trap the number more easily. This paper is dealing with terms that shrink at what's called a double exponential rate, which is just astonishingly fast.
Okay, and the final piece of the title, A Problem of Erdős and Graham.
Paul Erdős and Ronald Graham. I mean, you can't overstate it. These are absolute giants of 20th century mathematics. Erdős was, well, he was a force of nature, the most prolific mathematician of the century, famous for posing these beautiful, difficult problems.
And Graham was his close collaborator, a legend in his own right in combinatorics.
So when you see their names on a problem, two things. One, it's deep, it's not some trivial puzzle. And two, if it's been unsolved since they posed it in 1980, it's seriously difficult.
It has hidden teeth.
It really does.
Let's read the authors of this solution into the record.
The paper is by Kevin BARRETO, JIWON KANG, SANG-HYUN Kim, VJEKOSLAV KOVA:C, and SHENGTONG ZHANG.
And you can tell from the affiliations, which we'll get to later, this is a truly global team. We're talking Cambridge, Seoul, Zagreb, Stanford, all over the map.
A global human team.
Yeah, very important distinction. Okay, let's move on to the abstract, the very first sentence.
Answering a question of Erdős and Graham, we show that the double exponential growth condition.
Hold on. We've hit our first piece of formal mathematics, and as we said, under the unabridged protocol, that means we have to engage the perfect pronunciation protocol.
Understood. Time to be precise.
Yeah.
The condition they're referring to in the abstract is this one. It's a limit supremum.
Let's see it.
In LaTeX, it's written as lim subtento in 50.
And phonetically.
For the TTS, that is. The limit supremum, as n, approaches infinity of a sub n raised to the power of 1 over 5 to the n equals infinity.
Okay. We have to break that down completely. Let's start with a limit supremum. It's not just a regular limit.
No, it's a bit more subtle. A regular limit asks, does this sequence eventually settle down to one specific value? The limit supremum, or lim sup, is a bit more relaxed. It looks at the long-term behavior and asks, what is the largest value that the sequence keeps coming back to or getting close to?
So if a sequence bounces around, the lim sup is the ceiling it keeps hitting.
That's a great way to put it.
Yeah.
For this expression to equal infinity, it means the sequence doesn't have to stay huge, but it does have to have peaks that shoot off to infinity forever. It can't ever calm down.
And what about that symbol in the exponent, P. Jeller?
That is the Greek letter phi, and it stands for the golden ratio. The paper defines it right away.
The formula is?
It is phi equals 1 plus square 2.
Kinetic.
Phi equals the quantity 1 plus the square root of 5, all divided by 2. It's an irrational number itself, about 1.618.
Okay, so let's try to translate that entire mathematical condition into plain English. It's saying that the sequence of numbers, the Erdős terms, has to grow so ridiculously fast
that even when you take this massive, massive root of it, the e fuller to the nth root, it still goes to infinity.
This is what you meant by double exponential growth.
Exactly. You can think of an anfilar as growing roughly like some constant raised to the power of a feeler to the n. Just to give you a sense of scale, normal exponential growth is something like 2 to the power of n. This is like 2 to the power of, 1.618 to the power of n. The numbers become astronomically large almost instantly.
And the abstract says if you have a sequence that grows that fast, it's enough to prove what?
It's enough to prove the irrationality of a very specific series. And here's the series.
Okay.
The latex is something franquin and an an plus 1.
Let's hear it.
The sum from n equals 1 to infinity of 1 over the product of a sub n and a sub n plus 1.
So you take these massive numbers, you multiply two of them next to each other in the sequence, take the reciprocal, and add all of those up forever.
And the claim is, if the n's grow according to that lim sub condition, the final sum is guaranteed to be an irrational number.
Wow. Okay. The abstract continues. We also provide a positive generalization to, and then we see a more complicated looking series.
Yes, and this is a really key expansion. The original problem was just about pairs, right?
Yeah.
Times in plus 1. But here they generalize it to products of any length, which they call d $.
I see the expression here.
Let me read it. The latex for the generalized series is sum n 50 fratgan 21 plus d1.
And the pronunciation.
The sum from n equals 1 to infinity of 1 over the product of a sub n to the w naught through a sub n plus d minus 1 to the w sub d minus 1.
So those w's are like weights. You can raise each term in the product to a different power.
Exactly. It's like turning up the volume on certain terms. This takes the problem from one very specific question into a whole general theory about these weighted products. It's much more powerful.
And then the tone of the abstract seems to shift a bit. We prove a negative result showing that some of its instances are essentially optimal.
Yeah, a negative result. It sounds like a failure, doesn't it? But in math, this is actually a sign of a really great paper.
It's a good thing.
It's a beautiful thing. It establishes the boundary of your truth. They're basically saying, look, we proved this theorem works if the growth rate hits infinity. But if you relax that condition even a tiny bit, if that lim sup is just a finite number instead of infinity.
And theorem breaks.
It breaks completely.
Yeah.
You can actually construct a sequence where the sum turns out to be a nice, simple, rational number. It proved their theorem isn't just true, it's perfectly sharp. It's as good as it can possibly be.
It's like they've mapped the exact coastline between the rational and the irrational worlds.
That is a perfect analogy.
And then we get to it, the final sentence of the abstract, the kicker. This is the sentence that makes this paper historic.
Let's read it carefully. The original problem was autonomously solved by the AI agent Alethea, powered by Gemini DeepThink, while the remaining material is largely a product of human-AI interactions.
Autonomously solved.
That's the phrase. This isn't a paper where mathematicians use a computer to check a billion cases. This is a paper where the AI is credited as a discoverer.
It sets the stage for the whole rest of the document. This is not just a math paper. It's a logbook of a collaboration between carbon and silicon.
A whole new kind of science.
Okay, let's pause. Completeness check. That covers the title, the authors, and the abstract. We've defined irrationality, rapidly converging series, the golden ratio, limit supremum. We've gone through the pronunciation protocol for the key expressions, and we've established the role of the AI. Have we squeezed every last drop of meaning out of that section?
I think so. We've set the context of the Erdős problem. We've defined the double exponential growth. We understand the structure of the sums. I believe we have thoroughly unpacked the abstract. We are clear to proceed to section 1.
All right, part 2, declaration of AI usage.
And the placement of this is so telling. It's section 1. It's the first thing they talk about after the abstract. Usually you'd see something like this buried in the acknowledgments at the end.
It's a statement. They're saying the AI wasn't just a tool like a calculator or spell checker. It was a collaborator.
A co-author, in essence.
So they lay out a timeline of the discovery. We have to go through this point by point. Point 1.
Erdős and Graham posed question 1 below in their well-known 1980 problem book, expressing the belief that it should be solvable, perhaps by standard tools, and that some generalization should exist.
1980, that's 46 years ago. And they thought standard tools from back then should have been enough to solve it.
Which is fascinating because it means they were wrong about that. The problem sat there unsolved for almost half a century. It suggests there was some hidden twist, some difficulty that the standard analysis of the time just couldn't get a grip on.
Then comes point 2. The machine enters the story.
Alethea, a custom math research agent built on top of Gemini DeepThink, whose development was led by Tony Feng, found a solution to question 1.
But look at the detail they provide next. This is incredible. From the original output, it was clear that some generalization was possible. Specifically, the proof used rough estimates such as $1 7 valley, $22 pucks, etc.
This is so human-like, it's almost funny. The AI didn't find the perfect, most elegant, razor-sharp proof right out of the gate?
No, it found a sloppy proof, a correct proof, but a sloppy one. It used the fact that 1.7 is less than 2.
Which, as you said, is obviously true, but it's not tight. It's not the best possible number you could put there. It suggests the AI was focused purely on the logical structure of the argument, just finding a path, any path, to the solution.
Like hacking through a jungle with a machete instead of carefully pruning with a scalpel.
Exactly. Just wanted to prove it was possible to get to the other side.
Which then creates a job for the humans. Point 3.
The authors realized and proved that one can relax the original growth condition and generalize the series.
So the AI smashes the door down. The human mathematicians walk in, look at the mess, and say, okay, great work. Now let's clean this up. We can actually make this result stronger by making the initial conditions weaker.
It's a perfect division of labor. The AI had the raw conceptual power to see the path, and the humans had the expertise to refine it, to make it elegant.
But the conversation didn't end there. Point 4 is where it gets really interesting. Reciprocity.
Gemini DeepThink discovered a further generalization, and then, jointly with Alethea, proved it. This generalization corresponds to Theorem 3.
Wait, hang on. So the humans refined the AI's work, and then the AI turned around and generalized the human's work.
Yes, it's a feedback loop, a dialogue. The AI came back with an even more powerful idea, that complex polynomial with the weights we saw in the abstract. That concept, Theorem 3, originated from the machine after the human intervention.
That's mind-blowing. And then point 5?
The authors found counterexamples that tightly complement the previously mentioned result.
This is the negative result again.
It is, and it seems to highlight a different strength. The AI was brilliant at finding what is true, at building the positive theory. The humans then came in and were better at finding the weird edge cases, the pathological examples that break the pattern and show where the theory stops being true.
So humans are still the best at trying to break things.
For now, it seems so. We're good at finding the boundaries.
And the final step, point 6, is the final polish.
Inspired by Erdős, 1975, the authors were able to weaken the hypotheses further to obtain Theorem 3 below. So they went back to the old master, Erdős himself, found an idea in one of his older papers, and used it to make the AI's theorem even more elegant and powerful.
It's a beautiful synthesis. The section finishes with a really powerful paragraph about the methodology.
It says, this work also represents an interesting use case for AI in that it originated when Alethea searched over a large set of open problems and autonomously narrowed them down to those it could solve.
That's the real paradigm shift, isn't it? We're not just telling the AI, hey, can you solve this specific problem for me?
No, we're pointing it at the entire library of unsolved mathematics, all the open questions from the last century, and it is deciding for itself which ones look promising. It's setting its own research agenda.
Unbelievable. Okay, completeness check. We've gone through the timeline. Erdős poses the question. Alethea solves it roughly. The humans refine the solution. Gemini generalizes that refinement. The humans find the boundaries with counterexamples, and then there's a final polish. Is the methodology, this new human-AI interaction, clear?
It's crystal clear. We understand the back and forth, the dialogue, and we know that the writing, the final paper itself, was done by the humans, but the process of discovery was a true hybrid. I think we're ready for Section 2, the introduction.
Part 3, Introduction, Section 2.
So after that fascinating meta-discussion, we finally get to the mathematical meat. The section starts by formally stating the original problem. Question 1.
Let's read it. Is it true that if $A$A2 the need2.aldos is a sequence of positive integers with, and here comes the original condition.
Let's apply the protocol.
The condition in LaTeX is a left of there at most infinite.
And pronounced nets. The limit inferior as n approaches infinity of a sub n to the power of 1 over 2 to the n is greater than 1.
And the question is, if that condition holds,
then sum frac 1 and an plus 1 is necessarily irrational.
This is the seed for the whole paper. And notice the exponent here is 2 Bevel hours. The abstract generalized this to Finn, and later we'll see it get even more general. But the original question from Erdős and Graham was specifically about the base 2.
Right. It was a more concrete, specific version.
The paper then puts this problem in context. It mentions things like Ahmes series. What's that about?
An Ahmes series is it's just a classic sum of reciprocals, the sum of a longener. They're named after an ancient Egyptian scribe, Ahmes, because the Egyptians were obsessed with unit fractions. Erdős studied these kinds of series his entire career.
I see. And it also mentions Cantor series.
The Cantor series is a bit more complex. It's the sum of the form bottle divided by the product of all the terms up to 1 alice. The point the paper is making here is that these other types of series have been studied to death.
And there are results about them.
Yes, but those results often rely on extra assumptions. For example, previous work by Hanel and Tiedemann on similar problems required assumptions about relative growth, or more importantly, divisibility. Like, they needed R of t to divide on plus 1 time.
But this problem is different.
This problem is pure. It makes no assumptions about divisibility or any other arithmetic properties. It only cares about one thing. How fast does the sequence grow? The speed of the sequence is the only variable that matters.
That's a crucial distinction. Okay, let's move on to the first big result presented in the paper, Theorem 2. This seems to be the human refined version of the AI's initial proof.
It starts with a definition. Fix a positive integer dollars and let PSI 10 doll be the unique positive solution to PSI 1 plus ds.
Okay, that's a new Greek letter, PSI. What happens if we just plug in a simple value for dollars, like TS?
Well, if TS2, that equation becomes t squared equals d to the power of 1 plus 1.
So, PSI 2 plus 11.
Exactly. And that is the defining equation for the golden ratio. So in the special case where 22, this new number, is exactly our old friend Wood, this is a generalization of the golden ratio.
I see. So Theorem 2, Part 1 states, if a monotonically increasing sequence satisfies Lindell-Andiv, then the sum is an irrational number.
This is the positive result. If your sequence grows faster than this generalized golden ratio rate, the sum is guaranteed to be irrational. It's a clean, powerful statement.
But then comes Part 2, the flip side. For every dollars in 1 and 50, there exists a strictly increasing sequence, satisfying the limit equals $2 such that the infinite sum is a rational number.
And this is that beautiful tension we talked about. This is the negative result that establishes the boundary. It says if the limit is infinity, you get irrationality. But if the limit is any finite constant, $2, it doesn't matter how huge that constant is, it could be a billion trillion, you can always cook up a sequence where the sum neatly resolves to a simple fraction.
The phase transition happens exactly at infinity. Anything less, and all bets are off.
Precisely.
Okay, completeness check on Theorem 2. Have we covered all the bases?
I think so. We've defined DOD, we've shown how it connects back to the golden ratio for the simplest case, and we've really hammered home the critical distinction between an infinite limit leading to irrationality and a finite limit allowing for rationality. We're good to go.
Now for the big one, Theorem 3, the AI generalization.
That's right.
This looks a lot more complicated.
It is. This is where we get our hands dirty with those weights. It begins, fix a positive integer dollar and a tuple of non-negative integers W dollars, W1, dots, WD1, and then let capital dollar be the biggest of those weights.
And then they define this polynomial. This seems to be the absolute heart of the theorem.
It is. This polynomial is the engine. Let's get it on the record using the protocol. The definition is PDW1, D1, DD1, DW1, WJ, XGD, W1.
And the pronunciation.
P sub W of x is defined as the quantity x minus 1 times the sum from j equals 0 to d minus 1 of W sub jx to the j minus W times x to the d minus 1.
So why this specific complicated-looking thing? What's the point of it?
The point of this polynomial is that it perfectly captures the complex interaction between the weights you choose and the growth rate required for the theorem to work. Its properties dictate everything.
And what's its most important property?
In remark 4, they state that this polynomial has exactly one positive real root that's bigger than 1. We can call that root $.
And that's guaranteed.
It's guaranteed. You can prove it with something like Descartes' rule of signs. The function starts negative and then grows to positive infinity, so it has to cross the axis exactly once in that positive range.
So this root, $2, this is the new speed limit. It replaces the 2 from the original question and the t per c from Theorem 2.
It is the precise, custom-built speed limit for a given set of weights. The condition in Theorem 3 then becomes...
Let me guess. It's going to look very familiar.
It is. It's limit 50-50. And one anto in 50, phonetically, the limit supremum as n goes to infinity of a sub n to the power of 1 over c sub w to the n equals infinity.
So if that holds, and if another small condition on a numerator term holds, the big weighted sum is irrational.
Correct. That is the AI's big generalization.
Which brings us to Theorem 5, the negative counterpart to this.
Right. And here they introduce a subtly different polynomial. They call it tilde SPWX co.
How is it different?
The definition in latex is tilde CWX elco x D1 del ej less D1 del z.
Let's hear it.
P tilde sub W of x is defined as x minus 1 times the sum minus x to the d minus 1.
Ah, I see the difference. And the first polynomial, the last term was minus capital W times x to the d minus 1. Here, they've just gotten rid of the w.
It seems like a tiny change, just erasing one letter. But since w is the maximum weight, and it's at least 1, removing it makes that negative term smaller in magnitude. This, in turn, changes the root of the polynomial. The root of this tilde polynomial, which we can call tilde pseudo, will be smaller than the original pseudo.
And this theorem, Theorem 5, says that if you have a sequence that grows according to the rate of this new, smaller root,
then you can once again construct a sequence where the sum is perfectly rational. It belongs to the set math BVQ.
let's use example 7 to make this concrete, because it's getting a bit abstract. They pick a specific set of weights. 1W equals 1, 0, 2, $1.
Right. So for this specific choice, you plug the weights into the two polynomials. The first polynomial, the one for irrationality, gives you a root $2, which is approximately 1.916.
And the second polynomial, the tilde one for rationality,
That one gives you a root $, which is approximately 1.345.
so there's a gap, a whole range of numbers between roughly 1.35 and 1.91.
Exactly. A mystery zone.
So what does the paper say happens if your growth rate constant is, say, 1.7, right in the middle of that gap?
It says nothing. That's the boundary. The paper proves that if your rate is based on a constant above 1.914, the sum is irrational. If your rate is based on a constant below 1.345, you can find a case where the sum is rational. The space in between
Is left for future work.
or for Alethea version 2.0 to figure out.
Okay, completeness check. Have we clearly distinguished between Theorem 3, the big positive result for irrationality, and Theorem 5, its negative counterpart for rationality?
I believe so. Theorem 3 uses the polynomial p$ and its root 2 $, to prove irrationality. Theorem 5 uses the slightly different polynomial $2 and its smaller root $tilde to show that rationality is possible. The whole game is about which of these two critical growth rates your sequence obeys. The concepts are on the table. We're ready to enter the engine room.
Part 4. Proof of Theorem 3, Section 3. This is where we see how the sausage is made. We need to go through this lemma by lemma very carefully.
We begin with lemma 8. Mahler's criterion. The paper says, let zero be non-negative rational numbers. Let varying be positive integers such that zeri sum in zn lay is an integer.
Okay, so zeroing is basically a common denominator for the first n terms of the series.
Yes. And this whole criterion, which is attributed to Mahler, but as the paper notes, the idea goes all the way back to Fourier's proof of the irrationality of the number e. It's a tool for proof by contradiction.
How does it work, logically?
You start by assuming the thing you want to disprove. So let's assume our infinite sum, let's call it dollars, is actually a rational number. We'll say it's equal to p dollars. Now, consider the tail of the series. That's the full sum dollar minus the partial sum up to n. If you multiply this tail by our big common denominator, d dal every, you get an interesting expression. And if Zila's is rational, that expression should eventually become an integer.
Why an integer?
Because dLidels is built to clear out all the denominators of the partial sum. And if we pick it large enough, it will also contain the denominator $2 from our assumed rational number, $7. So dollar times the is an integer, and dollar times the partial sum is an integer. The difference of two integers must be an integer. But, and this is the whole trick, if the terms of the series shrink insanely fast, that tail is so microscopically tiny that even when you multiply it by the huge number dln1, the result is still a positive number that is strictly less than 1.
And there are no integers between 0 and 1.
There are no integers between 0 and 1. That's the contradiction. Your assumption that 0 is rational must have been false.
So the entire strategy of the rest of this proof is to show that this one quantity, the denominator, times the tail goes to 0.
Exactly. That is the goal. And that goal is stated formally in Proposition 11, which we'll get to in a moment.
Next up, lemma 9, Borel's trick. It says, if Delton and Alman-Alna are positive sequences, then the set mathcal of indices where mum plus 1 jumps is infinite.
The inequality here is mum plus 1. In simple terms, it's saying that if you have a sequence that goes to infinity, it can't just creep up there smoothly forever. It has to have these moments of sudden growth, these peaks, where a new term is significantly larger than anything that has ever come before it.
And we need these peaks for the proof.
We absolutely need them. The peaks are the moments where the terms in the series get so huge that they can crush the tail of the sum and drive it towards 0. The proof relies on these jumps.
Okay, on to lemma 10, Vinogradov notation in dyadic blocks. First, that notation, phi FESLXX.
That's just standard shorthand in this area of math. It means Pfeffersos is less than or equal to a constant times gx. It lets you ignore irrelevant constants and focus on the main behavior. In our phonetic protocol, we'd say f of x is bounded by g of x.
And then it talks about splitting the sum into dyadic blocks, which it calls ij. The formula is...
Since a chance q r, 2j is q plus the formula
The
is...
set I of j is a set of k, such that x sub k is between 2 to the j x sub q and 2 to the j plus 1 x sub q.
So why are they doing this? Why not just sum everything up from 1 to n? Why this complicated block structure?
Because we're dealing with double exponential growth. The terms are changing scale so unbelievably fast that n plus 1x practically in a different universe from a dx. You can't just add them all up in one go. You have to group them by orders of magnitude, by doublings. By controlling the sum on each of these blocks, they can get a handle on the total sum of the tail.
I see. And the lemma has two parts. Part 1 says if the terms grow at least polynomially, the sum converges. Part 2 says if they grow exponentially, it converges even faster. Right. And we'll need both of those results depending on how the sequence is behaving in the different cases of the proof.
Completeness check on lemma 10. Do we understand why they're using these dyadic blocks?
I think so. It's a management technique, a way to tame a sum that is growing far too wildly to handle all at once. We're ready to see how they use these tools.
Okay, now they set up the main variables for the attack. We have log and a CNOs. We have 6 sexes, that weighted product. And we have the big one, propay n AKAO.
And pay close attention to that d on a d on. That's our candidate common denominator for Mahler's criterion. It's a gigantic number. The entire proof now hinges on showing that the tail of the series, which they call Wanna-Nettles, shrinks even faster than the DNE day grows.
Which brings us to proposition 11.
This is the bullseye. The entire proof of Theorem 3 is reduced to proving this one statement.
And the statement is, lemon dn Rna equals Muller's dollar.
The phonetic reading is, the limit inferior as n goes to infinity of d sub n times r d on a is 0.
So, if they can prove this, that the product of the huge denominator and the tiny tail goes to 0.
Then Mahler's criterion from lemma 8 kicks in, gives us the contradiction we need, and proves the number is irrational. Game over.
And to prove this proposition, they need another tool, lemma 12, local peaks. This looks like a beast of an inequality.
It is. It starts with, suppose we have indices Q2 docs such that MQ plus 1, 1 plus delta Q max MUC. This is just saying we're at one of those special peak moments from Borel's trick.
And the conclusion is?
The conclusion in latex is AQ2 WXQ plus 1, 1 Q2 plus 1.
Can we get that phonetically and then in plain English?
Sure. The product of AP through a Q to the W times X sub Q plus 1 is less than or equal to 1 over a sub Q plus 1 to the 1 over Q squared plus 1. What it means in English is that at these peak moments, the next term in the sequence, AQ plus 1, 1, is so colossally large that it completely overwhelms the accumulated product of all the previous terms.
It's like a tsunami washing away a sandcastle.
That's a perfect image. The sandcastle is our denominator, DDM day. The tsunami is the rapid decay of the series tail, which is driven by this new enormous term. This lemma proves the tsunami always wins at the peaks.
So now finally, the proof for proposition 11, they split it into 3 cases.
Right. We have to check each one. Case A is the easy one. This is the case where the sequence just... the condition is 6 ballers plus 1 gedge DNMM. The next term is already way bigger than the denominator.
So the tail is tiny.
The tail is microscopic. They just apply lemma 10, part 1, and it shows directly that 0 DNM and anal goes to 0. This case is, in a way, trivial.
Then case B. This is where the sequence grows, at least exponentially, so all j.
Here, the growth isn't quite as wild as in case A, so they need to be more clever. They use lemma 10, part 2, and the local peaks, lemma 12. They look at the logarithm of the expression they want to control.
And what do they find?
They find an inequality. Log dn plus 1 and 2 plus 1 plus 1 plus 1.
Yeah.
And since bigger than 1 and the most sequence goes to infinity at the peaks, that main term goes to negative infinity.
And if the logarithm of a number goes to negative infinity, the number itself must be going to 0.
Exactly. Case B is done.
Which leaves case C, the neither case. This is where the sequence is being difficult. It isn't always growing super polynomially, and it isn't always growing exponentially.
This is the tricky one. This is where the proof really shows its strength. Since the terms aren't behaving nicely one by one, they have to look at the behavior of entire blocks of terms.
This is where those peaks come in again.
Right. They define a special set of local peaks called math.CA when they take the tail of the sum and they split it into 2 pieces. They call them sigma 1 and sigma 2. Sigma 1 contains the terms that are near one of these peaks.
And sigma 2 is everything else, the terms far away.
Yes. And then, through a series of very careful estimates, they prove that both pieces, when multiplied by DD and all, go to 0.
And if both pieces go to 0, their sum goes to 0. From the splitting, we conclude limit if dqrq equals 0 is Euler.
And that is the end of the proof. Proposition 11 holds, which means theorem 3 is true.
Wow, okay. Completeness check. That was a marathon. Did we follow the high-level logical flow of that proof? From Mahler's criterion to Proposition 11 and then through the 3 cases, A, B, and C, that prove the proposition.
I think we did. We saw the main tools. Mahler's criterion to set the contradiction, Borel's trick to guarantee peaks, and Vinogradov notation with dyadic blocks to handle the sums. Then we saw how case A, super fast growth, case B, exponential growth, and case C, the tricky irregular growth, all lead to the same conclusion. The denominator times the tail vanishes. The logic is sound.
Then let's switch gears completely. Part 5, Proof of Theorem 5, Section 4. We are now leaving the world of irrationality. We're on a mission to prove that rational numbers can exist if the growth rate is just a little bit slower.
It's a totally different kind of argument. It starts with lemma 14, which is a very technical-sounding lemma.
Let's hear it. Let bitnan and n be sequences. Then the set of infinite sums is equal to a finite union of non-degenerate closed bounded intervals.
Okay, what on earth does that mean? It's based on something called an interval argument.
Break that down for us.
Imagine you're building your sequence other than $, but at each step, you don't pick a specific number. You're allowed to pick any integer between a lower bound, Bettenauer, and an upper bound, gammon.
So you have some wiggle room at each step.
A lot of wiggle room. Now think about the set of all possible final sums you could create by making all these different choices. The lemma says that if your bounds Batan and Allenal are chosen correctly, this set of all possible sums isn't just a disconnected mess of points. It actually smears out to form a solid, continuous chunk of the number line, a nice solid interval.
And if you can prove that the set of possible sums is a solid interval,
then you've won. Because the rational numbers are dense. They're everywhere. You cannot have a continuous interval on the number line, no matter how small, that doesn't contain infinitely many rational numbers. So if you can form an interval, you've proven a rational sum must exist within it.
So the strategy is inductive. They show they can pick the honor terms one by one to steer the final sum toward any number they want within that interval, including a rational one.
Exactly. The key is to check inequality, 4.8 in the paper. It basically makes sure that the intervals of possible sums you can make at step n plus 1 overlap with the intervals from step n. As long as they overlap, you don't create any holes or gaps. You get one solid, continuous set of possible outcomes.
And then come the final proof steps of Theorem 5. They have to choose those boundary sequences, Batan and gammon.
And they choose them based on the root of that other polynomial. The root Demon tilde crunch.
The one for rationality.
The one for rationality. They show that if you define your growth rate using the slightly smaller constant, the conditions of lemma 14 are all met. Specifically, a certain limit in their calculations goes to infinity, which is the technical condition they need to guarantee the intervals will always overlap.
And therefore, a rational sum must exist.
It must. It's an existence proof. It doesn't tell you what the rational number is, but it proves one has to be in there somewhere.
They mention one final minor detail. The sequence they construct might not be strictly increasing at the start.
Right. In their construction, you might get Fate 5 always as 66 or something. But they point out that changing a finite number of terms at the beginning of an infinite series doesn't change the final sum.
No, it just changes the rationality. Wait, no, it doesn't.
It doesn't. If you add a rational number, the sum of the first few terms, to an irrational number, the tail, you get an irrational number. If you add to a rational number, you get a rational number. So the tail is all that matters. They can just fix the first few terms by hand, say, set one out for the first $1 million terms, to satisfy the strictly increasing condition, and the rest of the proof about the tail holds.
Completeness check. Do we understand this fundamentally different proof strategy for rationality?
I think so. Instead of a direct proof by contradiction like in Theorem 3, this is a non-constructive existence proof. They prove that the set of all possible sums is a solid interval. And since every interval must contain rational numbers, a rational sum must exist. The logic is sound.
We are in the home stretch of the Unabridged Protocol, Part 6. Acknowledgements and references.
We can't skip this. We have to acknowledge the humans and institutions that supported this incredible work. Let's start with the funding.
The third named author is supported by Mid-Career Researcher Program, National Research Foundation, Korea, KS grants.
The fourth named author is supported by the Croatian Science Foundation, Project FING.
A lot of public funding from Korea and Croatia making this possible. Now for the more personal human touches.
We thank Thomas Bloom for creating and maintaining the website Erdős problems.
That's a great resource, a digital library of all these unsolved challenges.
And then a big name appears. Thanks to Terence Tao for valuable comments on an earlier version of this paper.
Wow. Terry Tao, often called the greatest living mathematician.
If he read an early draft and gave comments, you know the foundations of this paper are absolutely rock solid. That's the ultimate peer review.
And they thank the AI team, of course. We are thankful to the authors of 10 for building the Alethea agent. I looked at reference 10. It's a list of 27 authors from Google DeepMind. Tony Feng, Thao Trin, Edward Bingham. It takes a village to build an AI like this.
It's an army.
Let's list the affiliations. Queen's College, Cambridge, Seoul National University, the Korea Institute for Advanced Study, or KIAS, the University of Zagreb, and Stanford University.
It's a map of global academic excellence. The UK, Korea, Croatia, the US, and of course the digital nation of Google DeepMind.
We have reached the end of the document. The unabridged protocol is now complete.
Protocol deactivated.
That was intense.
It really was.
Yeah.
But let's just take a second to recap the journey we just took. We started with a question posed in 1980 by two legends, Erdős and Graham.
We saw how an AI agent, Alethea, cracked the case nearly half a century later using a clever but rough proof.
Then we saw how its human collaborators stepped in, refined that proof, and generalized it into Theorem 2, connecting the problem to the golden ratio.
And then came the feedback loop. The AI, Gemini DeepThink, pushed back, generalizing the human's work even further into the powerful Theorem 3, driven by that custom-built polynomial.
We walked through the brutal logic of that proof. Mahler's criterion, the dyadic blocks, and the three cases that harness the crushing power of double exponential growth.
And finally, we saw them map the boundary of their discovery with Theorem 5, proving that if you just slow that growth rate down a little bit, the certainty of irrationality dissolves, and the world of simple rational fractions becomes possible again.
I mean, we just read a blueprint for what the future of science and mathematics is going to look like. It wasn't AI replaces the mathematician.
No, not at all. It was a conversation. Mathematician asks, AI answers, mathematician refines, AI generalizes, mathematician challenges. It's a dialogue.
It really is.
And for you, the listener, if you are still with us after all that, you have stared into the abyss of an infinite sum, and you have seen the incredible, intricate structure at the bottom.
So here's a final thought for you to take away. We talked about that gap, that mystery zone between the constant dollars that guarantees irrationality and the smaller constant tilde that allows for rationality.
The paper leaves that gap completely unexplored. What kind of numbers live in there? Are they all irrational? Are some of them rational? Are they algebraic or transcendental?
Alethea hasn't answered that. Not yet.
And you can.
Or maybe you can ask the next generation of Alethea.
Thanks for diving deep with us. Now go calculate some partial sums. We'll see you in the next epoch.